So, good morning again. Thank you very, very much for joining us here. And welcome to the European Space Agency and welcome to ESTEC, which is the European Space Research and Technology Center. We are, that is the picture from above of the site, and circled is this building. So you see this is just a small part of a much larger site. It's the largest establishment of the European Space Agency with almost, I think, around 2,500 people on site. We basically follow the pre-development, both from a technological and system science point of view, and then through the design, even the testing, and then the exploitation of the data, basically following mission from cradle to grave, as we used to say. But also welcome to the third workshop on international cooperation in spaceborne imaging spectroscopy. I sincerely apologize for the acronym. This was a nightmare. I will never use it in public, but WIXIS or whatever was just a way to have a very short way to reference to it in the subject, because otherwise the name would have been too long. This, as many of you know, is a series of workshops. We started in 2019, and then in 2022 in Frascati in Italy, and this time is the first time we are organizing that, the first edition outside Italy. So we know for sure you're not here driven by chasing food or good weather, but I hope that the Netherlands will also be able to surprise you a bit over these days, possibly on both of these elements. This is also the first edition where we open participation to all, let's say, willing registered participants instead of on an invitation basis. And also this time in a location which allows basically double the number of participants than last time. And we reached almost full capacity. We will be 190 in-person participants plus a number of people, I think currently more than 50 registered for following online. This is not meant to be a hybrid event. It's an in-person event with lots of discussion, interactive session, but we gave also the possibility to people who could not travel to follow remotely from WebEx in a listening mode. So welcome also to those of you who are following online, of course. As in the past edition, we really want to focus this workshop on cross-cutting elements across missions, across domains, across product levels. And we want to focus on being complementary to other key events for the imaging spectroscopy community. For example, EarCell with a workshop driven by the Special Interest Group on Imaging Spectroscopy, Living Planet Symposium, WHISPERS, and just allow me to spend few seconds to give our warm thoughts and best wishes to the people and city of Valencia who hosted the last EarCell imaging spectroscopy workshop and is now undergoing really tough times. And I see also some faces from institutions in Valencia present here. So thank you even more for joining us in these challenging times. And I think I speak for everyone in wishing you the best wishes to recover swiftly from this tragic event. So the format of the workshop, as you've seen from the agenda, is focused on very short presentations, and we also selected on limited number of presentations compared to other events. We will have poster sessions, but most important, we will have time for discussion at the end of each session, and breakout session tomorrow afternoon. We will see later in the agenda more in details. We really we will reiterate this message over and over again. We have to ask you to stick to the timing for the presentation, because we absolutely want to preserve the time for discussion. This is the reason why we asked you to come here in person. This is really the most important element of this workshop. The question and answers, the discussion, the interactive part, which culminates tomorrow afternoon in the 2 hours breakout session. Yeah. Finally, I want to highlight that we are here at the European Space Agency, but this is really not just in the banner, but also in the reality of the organization and the support to this event, a joint interagency event where the ASI, DLR, NASA, and ESA were really equally involved and pushed through the organization in the last month. So I want to thank very much the members of the organizing committee, basically representing all agencies and beyond, for the continuous work that over the last several months to put together this program and make sure that we have all the elements to come up with some concrete output at the end. And also, of course, the members of the scientific committee who supported the selection of abstracts, shaping the sessions, and now also sharing them during the event. So thank you very much to all of you. And unfortunately, not everyone could make it in person. Some people hopefully managed at least to listen in from the WebEx. But we have to accept that not everyone could make it in person, including Simonetta Kelly, Director of Earth Observation Programs at the European Space Agency, who could not be here due to other commitments, but sent us a welcome message, which we would like to display. And in the meantime, I would kindly ask Amit, Laura, and Luigi to come close to stage.
As Director of Earth Observation Programs at ESA, I would like to welcome you all to the third workshop on international cooperation in spaceborne imaging spectroscopy, organized by the European Space Agency in collaboration with our esteemed partners, NASA, DLR, and ASI. I'm sending to you this message by video because, unfortunately, I cannot be with you today. But I would like to thank you all for joining my colleagues at ESTEC as we continue our collective efforts to explore the frontiers of Earth observation through imaging spectroscopy. From monitoring vegetation and soil health, biodiversity, ecosystem functioning and water quality, to mapping raw materials and anthropogenic greenhouse gas plumes, spaceborne imaging spectroscopy is key to addressing the global challenges we face, from climate change to food security and sustainable development. This workshop marks a significant milestone in our ongoing mission to enhance scientific collaboration, technological advancements in Earth observation. ESA has always recognized that global challenges require global solutions. By working together with leading space agencies like NASA, DLR, and ASI, we combine our strengths, expertise, and resources to push the boundaries of scientific discovery and application. In recent years, the launch of DESIS, PRISMAS, ENMAP, EMIT, and PACE has increased tremendously our access to imaging spectroscopy from space, paving the way to future operational missions like CHIME and SBG. By acting together, we will enhance our global understanding of the planet, ensuring that the insights we gain are both actionable and accessible to the global community. This workshop is a perfect demonstration of that principle in action. Over the next few years, you will focus on several key areas such as fostering synergies between current and upcoming spaceborne imaging spectroscopy missions, strengthening the interoperability of data from different missions, ensuring that researchers and policymakers can drive maximum benefit, sharing our collective experience and expertise to address the technical challenges and innovation in this rapidly evolving field, exploring how the data we collect can be applied to real-world problems and contribute to the broader goals of sustainability and planetary health. I'd like to thank you, all the participants, speakers, and organizers for making this workshop possible. Your dedication, your expertise, your passion for advancing science are what drive progress in our field. I'm confident that the next few days will be filled with fruitful discussion, new ideas, stronger collaboration. Let us continue to work together to unlock the full potential of spaceborne imaging spectroscopy. Thank you, and I wish you a successful and inspiring workshop.
So virtual thank you to Simonetta, of course, and we have here represented really a number of space agencies, and we would like to give the chance to express a couple of words of welcome words also to our colleagues from ASI, from DLR, and from NASA and JPL. So I leave the floor just for a couple of minutes to Luigi, and then Laura, and then Amit, please.
So, good morning. I am Luigi Ansalone. I'm a space engineer of Italian Space Agency. A kind warm welcoming for you from the Italian Space Agency and from Francesco Longo, the head of the Earth Observation Department, that cannot be here, unfortunately. So I'm very happy to be here. I think that this workshop is a very good opportunity to exchange ideas, to update the community for what we are doing and where we are going for our missions. So it's very nice to be here. It's very nice to meet a lot of people, a lot of old faces and new faces. So it's very nice to see you all. So thanks again. I will pass the floor to Laura.
Good morning also from my side. I'm Laura Lapota. I come from the German Space Agency at the German Aerospace Center. As you know, we have the MED mission running. I'm the mission manager, and I'm very happy to say that we had a very successful year. The user kept giving us positive feedback about the data, confirming the high quality of this data, and provided also very nice example of the application that can be achieved or can be supported with high quality hyperspectral data. Not only for pure research, but also for application that have a social value. Just to mention a couple of examples, the possibility to quantify the methane leak that occurred in Kazakhstan during the past months and was one of the largest during the past years, or the possibility to identify the best drilling position for raw materials. In order to be able to exploit at best the potential of the hyperspectral data, we really need to join forces and to use the synergies among the various missions that are producing hyperspectral data. And in order to be able to do that, we really need a strong community. So we need to have a very good flow of information among the experts that are working in the field of hyperspectral remote sensing, not only from the academic world, but also from the commercial side. And in order to do that, we really need these kind of workshops. So this gives us a unique opportunity to improve networking and also to either strengthen or create new cooperations. So we thank again the organizer for giving us all this possibility, and we look forward to fruitful discussions among us all.
Thank you, Marco. Good morning. I just want to stand over here and talk a little bit, if that's okay. But I'll just have to tell you, this is a privilege to come over here. No, I did not come for the food or the weather, but I came for you all to work together in this wonderful endeavor that has been collected. So, well, as Marco pointed out, it looks like I've been participating in these events since 2019 and before, right? And we took a little break because of the COVID situation, and then now we are back. My name is Amit Sen, and I am from NASA JPL. And I also have the privilege to lead a wonderful group of people for SPG, especially in the visible shortwave and infrared area. So, and I'll tell you just a bit about it because you've got more sessions coming out and to give you an update. But just to capture a little bit from the NASA perspective, this is a direction that we have been taking since our decadal survey, which is the Academy of Sciences, basically directed where the Earth science missions are going to go. And these 10-year decadal surveys that directs us to these missions. And NASA formed something called the Earth System Observatory, called ESO. And within that ESO, there are multiple different observations, as you know. And I will tell you, it is so important to us to say that SBG is one of the most important ones of that ESO candidates of observations and measurements. So SPG has been a very high priority for NASA, and we want to challenge ourselves to fit within the constraints of whatever has been given to us, resources, timeline, and other opportunities that we get. And what it means is, if you look around, it's you all representing the community. NASA does not forget its community and the support it needs to provide through the measurements. So we continue to do that. So our international partnership is very, very important. As always, we say it takes a village, right, to get this work done. It's not about one agency. It's about partnership and cooperation between the agencies that makes us successful and move forward. So, and I will not spend a huge amount of time because the whole focus of this meeting is about developing things. And I quote Marco's first statement, cross-cutting elements and being complementary. It's not that we do this and nobody else does that. We want to share our data, figure out the missions that we have. The best part of it is we're in a better time today than before. We have platforms up in space, right? Prisma, DASIS, Emit, and others, right? That we can test our algorithms and make sure that the future is coming forward with better prominence and better products that we can test, validate, and share amongst others. There's a rich set of applications that needs to be developed, and I think what better forum than to share it amongst others where we can benefit to the society and you all. So with that, I think it's the best way to look forward, and I'm looking forward to the next 3 days. And please come by and feel free to ask me whatever I can infer to you and give guidance to the team as I take back all this warmth and feelings that you guys have back to NASA. Well, welcome again. Thanks.
Thank you. Another round of applause for our dear speakers and colleagues. This also warms a bit your hands for the rest of the day. Yeah, that's okay. So okay. Thank you. You can just thanks. So it seems I coordinated with Amit, but I did not. So the headlines here are really in line with what has just been said, because it's true. We are living a spectacular moment in the history of Earth observation in terms of not just what has been, let's say, developed, but also in terms of accessibility to the data produced by these missions. And imaging spectroscopy is a great example for that. In the past 5 years, as you know better than me, the increase in availability of imaging spectroscopy measurements and products from space has increased tremendously. And the missions that Amit has mentioned are an example of that, together with few others. I think that this testifies the tremendous investment from the space agencies, from the public sector. We know that there is a tremendous investment ramping up also on the commercial side, but also, and I want to stress that, from the community who pushed for that since 40 years aside the space agencies. And we have great examples of early, let's say, let me call them early success stories that we are living today, both in the educational tools that agencies and communities have developed in terms of early scientific exploration programs to maximize the return of these hyperspectral measurements, to upcoming and actually ramping up, starting now, programs for preparing the applications which will be made available by the increased availability of operational products in the near future. But we've also seen very recently the first regional to global scale products coming up of imaging spectroscopy. This is something which was hard to predict a few years ago, perhaps. And I look at some of the faces in the audience who made that possible. It's really spectacular. But it's clear that there is a mixture of opportunities and challenges ahead, both for you as a community, and so the availability of, for the first time, of, let's say, imaging spectroscopy, time series from space is a clear first in history, let's say, opportunity. Regional scale coverage, the increased visibility and recognition to the community which this brings, and the products that are developed out of this bring. But also challenges linked to accessibility of all these different streams of data with different portals, different data formats, perhaps slightly different specifications. For some of these missions, I mean, which are tasking missions, not carpet mapping missions, like CHIME and SPG aim to be, there is to some degree a lack of predictability if a certain acquisition will be there or not when you need it. Also, I mean, the increased availability of this large amount of data sets, complex to handle large amount of data sets, put pressure on storage and computational resources for those who have to handle these data. But these are also, let's say, some of these are common to opportunities and challenges which the space agencies face, because combining all these sources together means that we will have collectively an increased revisit or coverage from the collection of data streams from the different space missions, and also access to a larger user base, which is mutuated by the different communities linked to the different missions, and also access to algorithms which are developed for one mission, but can be, to some degree, we will discuss a lot about this, applied or useful also for other imaging spectroscopy mission, and the increased outreach which comes out of that, right? At the same time, different user bases, different user communities behind different missions means different user needs. So this means that each of the missions may have been designed for a slightly different use case and primary objectives, and this brings difference, maybe slightly difference in the specifications, in the key requirements of these missions which have to be handled. Also, storage and computational resources, I tell you, are a challenge for space agencies to handle this increasingly large and complex amount of data. And also, back to the tasking missions, I know that particularly some of you will be very familiar with the challenge to handle user requests for new acquisitions which conflict to each other. So how do you prioritize what you do in that cases? So it's certainly a mixture of opportunities and challenges that we want to focus on, to tackle, and perhaps to, well, if not finding a solution, but at least paving a way forward during these 3 days. And with this, I leave the floor to Anke Schicklin.
Good morning, everyone. Also, welcome from my side. So, when we consider the recent developments and the current status and data available of the different missions and also the upcoming missions, we set the objectives of the workshop to the following. So basically assess the current planning of the international imaging spectroscopy missions, identifying major, also minor gaps and opportunities for the scientific user community, especially considering the development of the future imaging spectroscopy missions. And as mentioned already several times before, also from our colleagues, to strengthen the international cooperation for the space and the ground segment in respect to the calibration validation, product definition, data access, and also data exploitation. So basically all the subjects we will cover in the different sessions. So in order to achieve these objectives, we tried to choose a very interactive format of a workshop. We have 2 interactive elements. So basically, at the end of each session, we will have a Q&A and discussion slot. And in addition, on Thursday afternoon, we will have breakout groups for different topics. So we want to focus on the calibration and validation. This breakout group will meet here in the high bay. We have another topic covering the product harmonization and instrument agnostics. This group will meet in the auditorium. And a third topic on open science development, also including the open source and the open data. Now, of course, you noticed immediately that the topics of the working breakout groups do not match all the topics of the session. This is basically on purpose. So we do not have a dedicated breakout group for the high-level global product development. But this is on purpose. So we asked the participants of this session to contribute to the other sessions. So basically talking about their challenges they have in the dedicated sessions. So if you think that a lack of calibration and validation is a problem for a higher level product, please join this session to express your concerns there. And what is the outcome of this workshop? We already said we want to discuss a lot. And at the end, what we want to have is an updated set of recommendations from the user community, basically following what we had also in 2024, but assessing a bit, are the recommendations still the same? Do we have additions? Did we solve some of the problems already? So this would be our dedicated outcome. Now, before we start with the sessions, a couple of logistic things. You all received a PDF welcome package on Thursday evening. This contains a lot of useful information. Please have a look at it. It gives you all the information for the buses, everything related to the ESTEC sites, just to have a look there. All the sessions, everything will happen basically in this Erasmus building. However, we will not have the lunch here. We will go to the ESTEC canteen. So we will have the lunch at 1. We will all walk there together, so you don't get lost in the ESTEC area. And after lunch, we will all meet again at the ESTEC reception at 4:15 and walk back. Also, a short reminder, you're only allowed to walk by yourself with the visitors badges in the zone 1. This is basically the canteen, the coffee corner, but also the ESA shop if you want to buy a little present. So whenever you reach a door where you need an ESA badge, you're in the wrong area. Don't go there. As already mentioned, there are shuttle buses for the participants who booked their hotel in Nordwijk. They pick you up in the morning at some specific hotels and bring you back in the evening. For the schedule, also have a look at the welcome package. And also a short reminder, if you need to go to the airport on Friday afternoon, please book your taxi and your shuttle in advance. There's always a bit of a rush on the Friday, so just to make sure that you are there in time. Also some organizational parts for the workshop itself. So before each of the sessions, we have a coffee break, and we asked all the speakers to upload their sessions during this coffee break. Sabrina and Fabrizio, being there in the back, organizing everything for us, are basically there to collect your presentations, put them in the right order, so we have a smooth process there. So please, for the coffee break before, approach them and hand them your presentation. And also, maybe the speakers from the session could have a seat in the center of the first row, just to have a smooth process, because, as we said, we are quite limited with the time. So please, speakers, again, stick to your time. Also, the chairs, have a look that we do not run out of time, because we're really eager to preserve the time for the discussions. Let's go quickly through the agenda. So we are all in line. So basically, we are now at the welcome and introduction. Our first session this morning will be on the mission overview, followed by a Q&A session and a poster session. Then we will go for lunch together, and in the afternoon we will have the sessions on the instrument agnostics and the product harmonization. In the evening we will have a short icebreaker. This will unfortunately not happen here, because this building will be closed at 6 o'clock. But we will go to the winter garden close to the canteen, which is a very nice area, and have a drink there. The second day, we start with one of the biggest sessions, the calibration validation, which is interrupted by a coffee because, I mean, we need it. And also the open science development session will be before lunch. And in the afternoon, as already mentioned, we have the breakout groups. And then we encourage you after the official discussion and breakout groups to grab a coffee and also have a look at the posters. All posters will be displayed during the whole 3 days, just here in the back. So also in between, have a look, discuss with the people there, and then the bus will bring us to the social dinner all together. Last day, it's also our last session with the open challenges on the global products. And then we have a summarize and conclusion session where we ask the chairs of the breakout groups to give a summary, what were the results, the main points to be discussed, and hopefully come up with a new set or an updated set of the user recommendations. And then you're free to still have lunch here in the canteen or, I don't know, go to the airport or whatever your travel plans are. Now, one last thing, you need to have a look at a very serious safety and security video. So we all know what to do. And after that, we can start with the proper session. Thank you.
Welcome to ESTEC. In the unlikely event of an emergency, any kind of emergency, you can report it to the ESTEC security team from any internal phone by dialing 3333. From your mobile, please dial +31 715 65 3333. Emergency numbers and a site map can be found on the leaflet you were issued along with your security badge. Ignoring it is at your own peril. In case the building needs to be evacuated due to fire or any other kind of emergency, please follow your ESA host to the nearest exit. If you lose your way, follow the exit signs. To leave the building, do not use the lifts, only use the stairs. During the evacuation, refer to the ESTEC security guards and your host for advice. Once outside, move towards one of the assembly points, either the football field next to escape or opposite the test centre. Do not return to any of the buildings until the all clear is given.
Yes, so thank you very much. I think with that, we can grab another coffee and have a start of the workshop in time. Anything else?
Yeah, just a very final remark on the link to the agenda. On Friday morning, we will have a short report from the discussion, but then we really want to make use of this 2 hours or maybe most of these 2 hours to hear from you. Whatever is left over from the discussion on Thursday, whatever questions, whatever recommendations you may have. This is meant to be for all of you who will still be with us, hopefully most of you on Friday. This is not meant to be a one-way session, not just us telling you what are the summary of this workshop. So just wanted to point this out. And yeah, thank you very much again. And let's grab a coffee together. Thank you. So as you've seen or noticed, that we have digital and analog means to call you back to the sessions, and thank you for restarting in time. It's my pleasure to introduce the chairs of our first say real session. We have Jens Nicke from the European Space Agency, Rob Green from NASA JPL, and also Luigi Ansalone from the Italian Space Agency, who's speaking before. Without further ado, I leave the floor to the chairs, and thank you very much. Sorry, for the presenters, the the clicker is here on the podium.
Thank you, Marco. I'm sharing now together with Rob and Luigi. By the way, Luigi, where is he? I think he will come around very soon. We are sharing the session on the spaceborne imaging missions, the overviews. We have 14 presentations or 15 presentations, huge amount of presentations. We have to be strict in time. So we use analog versions in order to indicate, but we also stand up. So there are two ways of indicating that the slot is more or less over for your presentation. We start with a presentation by Giuseppe Bordi, and we are right in time in order to welcome Giuseppe for a presentation on the hyperspectral landscape. Rob, anything?
One quick thing, we won't have questions, so please save your questions at the end and at the beginning of the next session. If you have questions, that's the time to ask them.
And all the presentations will be online afterwards. So when we skip certain information as part of the presentation, don't worry, you will have it later on.
It's a go? Okay. So good morning, everyone. Thank you for the invitation to come here. So what I'm presenting is the results of a joint work we have performed in ESA to build an industry database of hyperspectral instruments and satellite. And we want to present to you a bit of the trends and the overview of what we have learned on this. So this is a work that has been done this year, as I said, jointly with the Directorate of Earth Observation and Tech, and it contains about 95 hyperspectral instruments. It's not fully complete, but I would say it's rather large. Both public and commercial missions are included. There are operational, planned, and also intended missions, so it gives a bit of overview in the past, the present, and the future. And for each one of the entry, there are operational and developer details, who is the instrument owner, developer, the mission, instruments, optical characteristics at certain levels, so not very detailed, the application and constellation information were available, and many other fields. So here is an overview of the main hyperspectral supplier worldwide. And you can see already from this kind of picture, but we'll see with data later on, that there is a kind of average situation between among the various continents. Okay? It's not complete, this list of logo. So some results and expected results we got from this database is that the commercial initiatives are dominating right now the number of instruments that are flying or planned to be flown. Up to now, we are about 78% of the instruments and satellites are commercially oriented. And you can see the progress into the graph on the right side. And of course, this is enabled by the so-called new space approach. If we break down this number by region, we recognize that there is a leading player, which is Satellogic, with a constellation planned of about 200 satellites, which is dominating in the period. But we see that in the past, let's say, North America and Asia were more present than Europe. Europe is starting to catch up this gap with the other regions. If you look on the satellite class, satellite size, also here we don't get big surprises. So commercial mission are oriented toward microsatellites up to 100 kilograms and public mission to large satellites. What we can see is that, or we listening the industry, we see there is a trend to go toward the mini satellite, which will enable better performance of the satellite right now, of the instruments, sorry, which are limited by the size of the platform at the moment. So if we now start to dig a bit into the performances and we look to the GSD, you see in amber dots the commercial instruments. We see that these are leading the journey toward the very small GSD down below 10 meters, and while let's say the public mission and instruments are still with very large GSD and also SWOT, which of course is explained by the different use cases. If you look into the application and GSD breakdown by application, if we see the land usage, the GSD is something like stable in terms of what is happening into the industry, while for the atmospheric, there is a tendency to go for smaller GSD to allow the identification of greenhouse gases emitters. This is a clear trend that we see. If we look into the spatial resolution, in the spectral resolution and other spectral parameters, actually we see a trend which is a bit counterintuitive. So since that the instruments are worsening, okay, is going toward a direction of spectral resolution which is not improving. And since this is explained by still the attempt to improve other parameters like the resolution at the expenses of spectral resolution, but I would this is just a temporary tendency, given by the, let's say, the explosion of the instrument that should go back. We should also say that spectral resolution, spectral parameters are very difficult parameters to get from industry and from so on. So the data set size is not so big to tell, yes, this is actually a confirmed trend. So to be very, very quick, I'm already to the conclusions. So new space instruments and constellation are increasingly pivotal for hyperspectral data production. So currently are dominating in terms of numbers. And what started in the past as a CubeSat and microsat just to demonstrate the capability, but with quality below the expectation, below what is needed, it has been recognized is not enough for the use cases, even for the commercial one. And this explains the trend now of the industry, also the new space toward better quality, better performance, and so on. New space entities are going towards smaller GSD. There is a startup in USA which is claiming 1 meter, which is, wow, which is more suitable for local case and regional case. And I'm not surprised, the public one are more looking for global cases. Spectral resolution remains a differentiator, so the quality of the instrument between the two groups, although, let's say, as I said, the data set is not huge to define a real trends, but we can see that that's what is happening right now. Okay? Thank you very much.
Thank you very much. Giuseppe stays with us also all day for any kind of question discussions, but questions in any case later on during the break. Uta Heiden, on status updates on the hyperspectral, oops, the title is gone, hyperspectral imaging archive of DESIS. Thank you, Uta.
Exactly. So, good morning, everyone. I would like to give you a short update about DESIS without rushing, hopefully, but it will be very quick. So if you have questions, please. I think we have a lot of coffee breaks. So you see here the model of the ISS. I think the DESIS instrument is on that side over there, and over there should be EMIT, right? So they are opposite to. Maybe we can. David suggested we can make stereo images for hyperspectral data. So it has been launched in 2018, and it's based on a cooperation between DLR, which is responsible for the scientific part, and Teledyne Brown Engineering, which is responsible for the commercial part. What you can see here, the green paths are the ground tracks from DESIS, and you can see it's not covering the whole terrestrial Earth, but we have a quite nice tilting opportunities, and with this we get almost 90% of the terrestrial Earth covered with our instrument. Maybe a few words about the specs. So one specific is it's from 400 nanometers to 1000 nanometer, and it has a very high spectral sampling rate from 2.55 nanometer. I think it's quite unique in the landscape of hyperspectral instruments we have currently in space. The target lifetime is until 2023, but the instrument is still running and active and so on. So we will continue, yeah, and I will say later some words about that. We have a couple of good products for the community. So we are delivering data in the level 1B, level 1C, and level 2A, bottom of atmosphere reflectance format. And it comes with a couple of image data about data quality, also in form of XML data. So it's actually very interesting and helpful, I think, for the data processing. Okay, how do you can access those data? In principle, I say in principle, you have three possibilities. There's an archive in a DLR, and you can access all data in this archive via the EOWeb platform. And then there's also a larger archive at Teledyne Brown Engineering, which you can access. And in principle, you can also task the instrument. In any case, if you're interested in those data, please contact desis-scientific@dlr.de, and basically you will come to me. And I say principle because since end of May, we have a hopefully temporarily stop of the mission because of an ongoing negotiation of Teledyne with NASA, and this process is still ongoing, but we have some good news, I would say. There's also, so I think a couple of weeks ago, we got the note that Teledyne has been selected by NASA as data provider, which is a very good step and first step towards the continuation of the mission. So the DESIS mission will continue. And so I also can say the instrument DESIS as well as the platform has been maintained since the stop of the operations by Teledyne. So they are alive and in good health. And we are regularly also checking the data, the calibration data that they are taking weekly. So that's also a very good sign. Teledyne also now slowly started to reactivate some of the standing orders. So standing order means we always look at a target whenever we are crossing the target and it's cloud free. And this is actually also one of the strengths of the mission that with this objective, we have a very frequent repetition on some of the sites, especially on those sites we have in the standing orders organized. So from our point of view, very good news. And also another good news is we never stopped at DLR, the services for DESIS, so you always can access the archive, explore it, you can also process the data. So we never stopped our services. Is that, I'm over? I'm okay. Just very quick, we are still working on making the data also available for bulk download. So currently it's not really handy for people that need massive data. So we are still working on it, providing it in web services, describing it in the stack metadata catalog, and so on. It takes a little bit of time because at the same time we would like to get the ARD standard from CIOS, but I think we can continue with this, yeah. And we have a special issue. It's extended until end of December. So if you're interested, please contact us. Sorry for being not in the 12 minutes.
Okay, now maybe, thank you. Thank you for letting us go quickly. We'll have a status on Prisma from Sarah Bentafra.
Okay,
Good morning to everyone. I'm Sara Venafra from Italian Space Agency, and with this presentation, I would like to give you a brief overview of the status of the PRISMAS mission at the turn of more than 5 years in orbit. Sorry. Okay. So as most of you know, PRISMA mission is an Italian Earth observation hyperspectral mission fully funded by Italian Space Agency and realized by Italian interests. The mission was launched on March 2019 and completed its nominal lifetime on last June. But it is already in a fully operational condition. As you know, the very important thing regarding PRISMA mission is the peculiarity to provide to the user co-registered images to hyperspectral data cube products. And also regarding the acquisition planning, these are oriented to serve the users in a different acquisition mode, such as on-demand for the primary mode, but mainly in a secondary mode regarding the background mission. For the data policy, we can state that we are in a state with quasi-open data policy because the products are given free of charge also for commercial exploitation since mid-2024. Okay, so in this graph, you can see the statistics of the users. On the left, you can see the statistic for registered users. A very large number of these users are presented at 16 of last September. And you can see that only 1/5 of these users are Italian users. This just to highlight that the mission is also well known and well appreciated also outside Italian borders. While on the right, you can see a graph regarding the user typology, which is most represented by scientists. And this is very important because PRISMA mission was conceived to be a scientific aim. In this slide, you can see the possibility to the user to choose the exploitation domains. The most selected one regard the agriculture, followed by land use and land cover, forest, and mineral mapping. In this histogram, you can see only the 70% of the all exploitation domains, because it was very impossible to have all the exploitation domains in this graph. So here you can see instead the archive. So in red, we have represented the pixels regarding all the images contained in the archive since the launch from 2019. And so you can see that all the land masses are well covered. And also regarding the archive quality, especially from a cloudiness point of view, in this graph you can see the percentage of cloudiness. You can see that almost 50% of the entire content of the archive has a cloudiness less than 1%. And the 13th of the entire content of the archive has a cloudiness measured than 50%. This means that the archive quality is very excellent. Then in green, you can see the measure area of interest, orders from catalog, and of course it depends on particular applications selected by the users, such as Italy site for PRISMA Scienza projects, hydrocarbons exploration in Kuwait site, methane detection from Texas, and so on. And so finally, just an application by Ettore Lopinto, which is the director of the mission, an application by using a pan-sharpening technique in order to highlight the importance of the mission in order to achieve a very high spectral resolution. Thank you.
Thanks, Sara. Now we have the presentation of Laura Laporta. Thanks, Laura. She will present EMMAP, the mission status overview and observing strategy. So, Laura, the floor is yours.
So, good morning, everybody. I come from the German Space Agency at the German Aerospace Center. We are responsible for the management of the mission, which is largely funded by our Federal Ministry for Economic Affairs and Climate Action. But clearly, these are the results of the work of a lot of people, a part of our consortium. And I invite you to give a look also to the other presentation from our cooperation that are actually, so will take place during the workshop, both from the scientific point of view, but also from the ground segment itself. Yes, no, I skipped one. Sorry. So this was a very good year for ENMAP. So you can see on the top panel, it's moving by itself, I'm very sorry. Okay. This was a very good year for ENMAP. You can see on the top panel a collage of some of the images of the data that were collected during the past months. And on the bottom, footprints of the coverage that we achieved so far since the beginning. The operation ran almost uninterrupted, and we acquired really about half of the data that are available in our archive. These very good results was possible thanks to the effort we made in the consortium. Sorry, I'm fighting with the, I'm fighting really with this remote control, which is the end already. Doesn't, where should it be pointed? Sorry, Marco. Okay, now it's going back by itself. Okay, that would be really great. Thank you very much. Okay, so these great results were possible through quite some changes and efforts in our consortium. Here, just to mention a couple, so we implemented a new feature of the mission planning system called back-to-back imaging, which reduces the minimum distance between consecutive data takes. Most important is also the extensive foreground and background mission that we carried out since this year. And we achieved an average number of data take per day, which is above our expectations, so the original requirement. We are now in the last quarter up to 188 data take per day. And we have in total more than 100,000 L0 products in our archive. Next, please. As I said, main contributor was the foreground mission. We started in 2024. We wanted to optimize our acquisition rate. So what we did was to select very long strides, about 1,000 kilometers, that were defined together with users in order to accommodate their needs. The workflow is still rather manual, so that indeed we can be rather flexible and react to weather changes and to some extent also to campaigns when we are informed of important ongoing ones. Here you will have also a poster from Nicole Pinel. You can have a look for more details. Next, please. Most contributor to the number of data that were required is actually our background mission. We started that already in 2023 with the goal of have time series, build time series, but also aiming at an aerial coverage. During 2024, we almost doubled the number of targets that are included in our background mission, and these targets, as you can see, are globally distributed. Next, please. In 2023, we started with, if you let me say, classical network size. In 2024, we added additional network size, but also specific targets that are important for some thematic application. Next. Most important, so I highlight from my point of view of the work done during the last months is the cooperation with ASI and with the PRISMA mission. We actually started concretely to work together. We identified more than 100 common acquisitions, which are globally distributed. And with the goal of develop L1 and L2 transfer function for multi-sensor time series analysis, we had regular meetings in order to agree on our target. And we started with this observation, 25 of which were actually successful and 10 of which have a cloud coverage less than 20%. So the workflow is well established, work is ongoing, and we invite you to get in touch with us if you wish to cooperate. Next. Okay, just to mention, we also did something for improving the accessibility to our data. Now it's not only possible through the official instrument planning portal, but also through the GeoService portal of DLR. And there you will find L2A data that have been produced with standard parameters. Next one, almost done. Okay, just outlook to the future. So we want to keep on with our program mission. We will move away from the north of Europe due to the bad weather. We want to keep in touch with the users by doing workshop in order to agree on the data, on the areas that are the more needed for the analysis. I draw your attention to our workshop that will be held at the beginning of April in Germany, close to Munich, in a very nice castle. We are going to have also visits of our ground segment facility and also of the industry. So it's really looking forward to that workshop. I hope to see you there. And again, I stress the importance of the synergies and cooperation. So we really want to become concrete and start working also with the other mission in order to get common data. Thank you very much.
Thank you very much, Laura.
Sorry for the problems.
Well done. Thank you very much. Next one is David on EMITS, lesson learned. Thank you.
All right, thank you all. My name is David Thompson. I'm Deputy Principal Investigator of the EMIT mission. I'm speaking on behalf of the entire EMIT team, including Rob Green, our PI, Natalie Mahowald, co-PI, Phil Broderick, Dana Chadwick, Regina Eckert, Nicholas Bone, others in the audience who are part of the EMIT team. We've learned a lot in the last 2 years of EMIT on orbit. That's the fortunate thing. The unfortunate thing is that works out to about 20 seconds per lesson for this talk, but I'll try and stay on time. So the EMIT mission was originally designated to map the geology of Earth's mineral dust forming regions to better understand the composition of mineral dust and thereby know more about the radiative forcing impacts of mineral dust on the climate system. And we do that from EMIT's vantage point on the International Space Station. It was launched and installed over 2 years ago now, so we've had plenty of time and operations to do this primary geologic mapping mission. But recently we completed that mission and have now expanded our target mask to cover other regions of the globe too. This is a map showing our coverage. The blue is areas that we have covered. There's some yellow that was at the time of this screenshot not yet delivered to the deck. Regardless, or the archive, regardless, you can see that we're expanding coverage over non-arid regions of the globe, including now into the tropical regions. And if you go to our website, you'll be able to download all of this data. Some places have been covered 20 or 30 times. So the first lesson I'd like to talk about is the feasibility of the Dyson design. EMIT uses a novel optical layout that includes some rather tricky to manufacture components like a grating that's written to a curved surface. It has a single cryogenic detector and a small number of optical components for maximum throughput. Other standout features of this design that we've now demonstrated on orbit include a high uniformity. Generally, it's spectrally uniform to within a couple of % across the entire wavelength range, which allows the most state-of-the-art algorithms to be used, and also a high SNR that came out rather close to our, close to our model predictions, as you see in the plot in the upper right, and a factor of 2 or more above our requirement for reasonably bright targets. So we're quite happy with the instrument performance and plan to use this design in future instruments. Another lesson, a related lesson, is that we've come a long way in terms of spectral fidelity. A combination of different technological advancements on the instrument side, the alignment side, better alignment strategies, calibration, both on the ground and in orbit, and also atmospheric correction algorithms have led the community now to a point where we can, over fairly typical conditions, get spectral fidelity that approaches that of field measurements. These are some examples from the EMIT archive, single pixels, unsmoothed, but not everybody in the broader community outside of this room is aware of that, and we need to keep evangelizing to other people who are still using benchmarks that could be several decades old. So this is a lesson that we take away for both ourselves and the larger community. Another lesson is that our onboard cloud screening strategy, designed to optimize our data downlink that we had from the ISS by screening out clouds on board with a simple band threshold algorithm, was definitely worth doing. We got about a 20% reduction in the total data volume. That's 20% more science data for the same bandwidth. But there's still plenty of cloudy scenes that were downlinked. And so we're looking in future iterations, future instruments to refine our onboard cloud screening to do an even better job of optimizing that downlink efficiency. Lesson 4 is that the Earth is an excellent calibration object. These are examples of calibration products that we were able to produce using only in-flight data, everything from fitting our spectral calibration to atmospheric features, to flat fielding, or radiometric calibration based on vicarious targets. EMIT has no onboard calibrators, and we're able to get an even better calibration result than our laboratory data using just in-flight data. Lesson 5, open source development has benefited the mission from the beginning. It's all been open source. This has broadened our community involvement and footprint and brought in many other users that have helped us advance our software more quickly. Lesson 6, we've identified many different global greenhouse gas super emitters. This is from a paper by Andrew Thorpe that does a sector-wide analysis across major areas of the globe. We have now delivered over 1,000 different greenhouse gas plumes to the US Greenhouse Gas Information Center to assist with mitigation. Lesson 7, continental scale mineral maps. You saw this from Marco earlier. Continent-wide mineral maps, mosaics, and that turned out to be fairly seamless. It turns out spectroscopy actually works. And this has led to an improved understanding of mineral dust radiative forcing. We've managed to significantly shrink the uncertainty in the mineral dust component of radiative forcing. It turns out to be a negative effect on radiative forcing overall, but that could change under future climate scenarios. It becomes slightly more positive in terms of radiative forcing. And then finally, spectroscopy is beautiful. We learn that wherever we point this instrument to create new maps, we discover the remarkable diversity of the planet, from minerals to the Amazon rainforest to aquatic regimes. We live in a beautiful place, and it's even more beautiful when you have eyes in the infrared. Thank you.
Thank you so much. All right, next we have an update on the PACE mission, NASA's most recent spectrometer.
Good morning, all. Thank you for the opportunity to be here and talk about PACE. We launched about 9 months ago. So after 20 years of pondering what this mission would look like, we are finally on orbit. For those of you who may be unfamiliar with us, nice glamour shot of the observatory and some general facts about it, polar ascending. I will point out that the primary instrument, OCI, and one of our contributed instruments, SPEX1, do fit within the theme of this workshop in the sense that they can do imaging spectroscopy. We're a little bit different than everything else we're talking about in the sense that OCI is a big 1 kilometer, 1.2 kilometer footprint, but it does offer near one-day global coverage. So I figured what I'd share, since the slides will be made available to you, and more about how you can get to the data and where we are with that. So we launched 9 months ago. Roughly 7 months ago, 60 days after launch, we made the decision to release radiometry from all 3 instruments, plus a couple of Heritage Ocean Color products. The cost of that, of course, is that what you're seeing isn't perfect, but wanted to get it into the hands of the user base. And we've already reprocessed the data twice at this point. The first reprocessing was in the early part of June, July, and that included the first use of on-orbit calibration plus a release of some advanced and non-heritage products, clouds, which are new to our group, and vegetation indices. And as we speak, we're conducting a second reprocessing. We've gone through the SPEX1 data set already. OCI will be sometime this month. We imposed a mandate that we do this before the holiday break. That'll include system vicarious calibration for the first time, which we're really excited about, and hopefully a release of some additional products as well. And then just to point out that going forward here, again, the data are in your hands. We hope that you are using them and learning and feeding information back to us, that the reprocessings that we conduct in 2025 and beyond will basically be when we're ready to do so. There is no formal schedule for all of that. But nevertheless, it's been a pretty exciting time. It's been a good year so far. So I want to point out 2 websites, and then I'll show you some quick results and then cede the floor. This is just for your reference. Given that the data are out there and we're well within the first year of launch, we do have a website and a series of release notes that try to point out what you might want to be cautious about when you use the data. So open there as best we can. So that's one that's worth visiting frequently as you get more familiar with our data streams. And then we're also throwing out our first wave of performance assessments as well too. So this will be in the package that's delivered. Consider going back often because we're doing our best to make sure everything is in your hands as quickly as possible. Okay, a couple other things then. So PACE is capable for terrestrial, atmosphere, clouds. I'm an oceanographer, and the original promise of PACE was to do phytoplankton community composition on global scales, and this is some reasonably hot off the press imagery. On your left is RGB, just what you would see if you were floating above the atmosphere. On the right is one of our early algorithms that separate 3 different dominant phytoplankton species here. So the different colors that you see each represent what is dominant in that area. And of course, this is unvalidated, but at the same time, it's the first time we've been able to do something like this pretty much on a daily scale. So that's really a nice win to be having. And this has not been shown publicly before, but this is our first attempt to put together a small time series using the same color bar of what this evolution of the phytoplankton community actually looks like. So we're trying to get some nice results out to the world so that you can tell us everything that's working, not working, and then show the promise of what this observatory can actually be doing. So with that, since I think I'm right around 5 minutes, I will have a walk-off screen, which basically indicates through PACE packs and the PVST down there. We also have field programs that are doing a lot of the work you might be interested in. These data will be available within weeks to months. And then we have an applications workshop and the Help Hub up there. Help Hub will show you how to get the data and also provide a lot of tutorials about use of it. So with that, I think I got to the 5.
Overview of Maya on the Platino Mission 4.
Yes, good morning. I am Luigi Ansalone, and I will speak on behalf of Matteo Picchiani. So, Platino 2 is our mission made in cooperation with NASA JPL, and it's a beautiful mission. To give a little context, Platino 1 is a SAR mission that will have monostatic and bistatic phases, while Platino 2 is in cooperation with NASA JPL. It's Maya. Platino 3, it's a VHR payload, while Platino 4, it's an hyperspectral payload. So talking about IRIDE, IRIDE is a program funded by the Italian government and made through a contract with ESA, and is a constellation of constellations. It will have an hyperspectral constellation among 60 satellites. There will be 4 satellites with hyperspectral payload that will be the recurrent models of our Platino 4. So let's talk a little bit about Platino 4. So Platino 4, it's a payload that goes from 400 to 2500 nanometers. It's like Prisma, but in a compact form. So Platino 4 will be around 90 kilograms of mass with the same 10 nanometers of spectral resolution. And it will have more or less the same performance of Prisma, so in terms of SNR and MTF, but with narrower SWOT. It will have 21 kilometers, and it will have a new form of acquisition called Spotlight that will increase the GSD up to 20 meters. While the Iridae constellation will be constituted by the hyperspectral part of the Iridae constellation will be constituted by 4 satellites that will operate our Platinum 4 payload. Obviously, there will be standard products between them, so there will be a very large amount of data we can expect. While Maya is a payload from NASA JPL, Maya stands for Multi-Angle Imager for Aerosols. We will provide the platform, and the payload will be provided by JPL. The payload has an instrument that moves inside, so while the platform stands in nadir pointing, the payload rotates with the 2 axes of rotation, the payload to acquire the same target with different angle of acquisition. The target of the mission is to track and have products on specific particulates. It will be a very it will be devoted to some specific targets on the planet. We will have some primary targets and then some opportunity targets or secondary targets with a grid of 1 kilometer. So they could work together because we can improve the spatial resolution of the synergy products, and we can help the retrieve of the spectral signature of the particulates thanks to the interaction between Maya and Iridium. So, thanks.
Here's the next one. All right, next we'll have an update on the truce radiometric strategy.
Okay. Good morning, everyone. I'm Thomas August, mission scientist for Truth, and here we go. I think the whole truth in 3 minutes. Let me start with a quick story, the story of the Maître. The Maître was born in Paris after the French Revolution. I don't know if you knew that. Until then, the reference for the metrics was basically the king or the queen to give the size of their feet or their elbows. And that was causing some issues because when the king or the queen was changing, then all the reference was changing, but also for international business or international cooperation, as we are here for today, because not all kings and queens have feet and elbows of the same size, obviously. So that was the reason for the Maître and how it got established as an international standard, immutable reference. The other innovation at the time is that they carved Maître in stones, literally, and put them in different places in Paris for the citizens to come and calibrate their tool, as we call them today, the users, calibrate their tools or verify if the products they had bought had actually 2 meters or if they've been cheated. And so let me come to this question to you. What is your in-space radiometric reference? What is your in-space Maître SI traceable? The truth is we don't have at this stage, and some of us are doing pre-flight calibration, investing in metrology protocols to have this SI traceability, which part of it will be lost during the launch or aging in space. And all of us are relying on vicarious calibration, as we've heard, and that's very good, and that's proven excellent so far, but with some limitation. And here is an example of Camille Desjardins, of the work she did. With vicarious calibration, we can demonstrate that Sentinel-2 and A are radiometrically within 1 or 2%. That's excellent achievement, and so are Sentinel-3A and B. But Sentinel-2 and Sentinel-3 are within 3 to 5% radiometric accuracy, which may or may not be an issue depending on your applications. Another vicarious calibration is using the moon as a target, and that's another example from Sebastian Wagner, EUMETSAT, using 3 different lunar models and showing that Sentinel-3A and B are indeed within 1 to 2% in all channels, but the 3 models are within 5 to 15% radiometrically, which is an issue. Where is the truth? So why does it matter? If we think of climate, the stronger the climate signal is, the shorter the time to detect if we have a perfect observation. The fainter the climate signal is, the longer it will take. If we add on top of that real observation uncertainties, then it takes decades at this stage with the instruments we have in space to detect trends, and that's too long for policy making. So, introducing TRUTH. TRUTH is designed as a metrology lab in space, aiming 0.3% accuracy to be launched in the 30s. And that's going to be the new meta in space you can refer to. TRUTH belongs to an international effort, the CITSAT, together with our American colleagues who are developing Clario Pathfinder. And it's there to support your missions, your applications, your services to bring them to the next level. So at this stage, we're seeing a lot of posts on LinkedIn. I have with my new hyperspectral mission detected methane leaks, for instance. But the next stage will be to quantify that with some SI certification. And that's the purpose of it. Yeah. So I'm nearly done. So the orbit of truth will give you a number of intercalibration direct observations, but as well as vicarious calibration sites, characterization of the moon, of the sun, of different sites. And here are some information for your reference later. You see that's a hyperspectral imager. You can come to that later. We'll just finish here. Thank you, truthfully.
Now we have Marco Celesti, and he will present the FLEX mission status.
Thank you very much. Welcome again. Here on behalf of a large group of people, as many of us, very briefly, FLEX mission objective is to basically retrieve full spectrum of solar-induced chlorophyll fluorescence from vegetation and other products related to non-photochemical quenching, and basically with the aim of quantifying actual photosynthetic activity of terrestrial ecosystems at global scale, and to provide indicators, physiological indicators for vegetation health status. Fluorescence is the best say proxy that we have about linked to photosynthesis, but it's a challenging, very challenging signal to deal with, particularly when you have to interact with the atmosphere on its way to the sensor measuring the reflected and emitted radiance from the surface, from the vegetation. For this reason, FLEX will fly in tandem with Sentinel-3 in order to get complementary information to better characterize the atmospheric state and also to better characterize the land surface properties underlying the measurements. This will be in a close formation, basically between 6 and 15 seconds, in order to maximize temporal co-registration between the two measurements. And very quickly, through some updates on the platform side, we are very advanced and ready to receive the FLORIS instrument for integration. The FLORIS will undergo calibration campaign early next year, and then shipment to Thales Alenia Space France for satellite integration. And all activities are running also on the preparation for the ground segment, the PDGS. The DISC, which is the Data Innovation and Science Cluster, is working really hard on, say, finalizing the development of the level 2 products, then implementing it into operational processor, preparing for the CalVal, and many more. So the official launch slot has been moved to 2027, but with the satellite and the ground segment ready by mid-26, we hope to have an opportunity to launch still in 2026, depending basically on the manifesto from Arianespace and for the Vega C manifesto. And with that, I thank you very much for your attention, and I point you also to Jose Moreno in the audience for any detailed question about science, as well as myself. Thank you.
Thank you very much, Marco. So we introduce now Kawashima-san from Tokyo University on the Japanese-born, space-borne hyperspectral sensor constellation project.
Thank you very much for introducing our project. My name is Kawashima from Tokyo University. So, okay. Okay, so this is overview. The small hyperspectral sensor satellite project is being newly developed under the Small Business Innovation Research SBIR program led by Japanese Ministry of Economy, Trade and Industry, METI, and scheduled for launch in 2027. So while the observation specifications are similar to those of IS-borne Hisui, the Japanese hyperspectral sensor on board the International Space Station. It aims to reduce both mass and cost to about 1/10 of the Hisui. So, okay, so we take advantage of the heritage of the conventional sensors, as well as we introduced a new technology, for example, monothetic spectrograph, as well as a E-wire detector technology. So the main specification is almost the same as the Hisui. The wavelength covers from V-near to 3-year region with the spectral sampling of the 10 nanometers, and GST is 30 meters, and the swath around 20 kilometers. But the size is only the 12 or 16 form factor with the 20 or 25 kilogram mass. This is a figure about the comparison between the Hisui and our new project, SBIR-SAT. Okay, I denoted before that the mass will be reduced by 1/10 compared to Hisui. And also both sensors implement push broom scanning. And the aperture of the SBIR-SAT is little smaller than Hisui's aperture, but the most prominent feature of the new project SBIR-SAT is the combination of the 3-year spectrograph and V-near spectrograph into the one spectrograph, thanks to the E-wire detector technology. Again, and mutualization will be realized by monothetic and okay. Yes, and the demagnification optics, which collect a large number of photons into a small detector with the miniaturized Turing system. And also, we implement onboard data reduction by cloud image removal. Okay, so last is the development plan. So engineering and flight model will be manufactured over the next 2 years, a very short development period. To shorten the development, and EFM method and EFM compatible with the FM will be manufactured, tested, and evaluated, and then refurbished in the flight model. Okay, so that is the main feature of the development plan. Thank you very much.
Thank you very much. All right, next we'll have a presentation on Prisma second generation.
So here we are again, Luigi Ansalone, and I'm presenting the status of Prisma second generation. So this is a new program funded by the Italian Space Agency, and it will give data continuity together with Platino 4 and IRIDE with the hyperspectral data to the community. It will be a complete new mission that will exploit the agility of the future platform. So we will have a new kind of observation, new products based on the agility on the platform. So we will have the SWOT enlargement, we can have the SNR enhancement, we can have stereo or 3 stereo image of the same target on the same pass. And we could also have a short revisit time based on a single satellite, thanks to the high roll maneuver capability. So we will have, as for Platino 4, 2 kinds of products: the strip map, like a normal push broom operation, and a spotlight product. The spotlight product is the more challenging one, the most challenging one, because we will go lower than 10 meters of GSD, and we will maneuver to get this performance. So the platform will have a GMC maneuver to observe, to slow down the velocity on the point on Earth. So What is the current status? We have started the contract with the long lead item procurements for the payloads. So the payload will be based on 1 telescope, 2 spectrometers, and pan cameras that will be different payloads. This design will exploit in a larger format the design of the Platinum 4. The mission will support the operation of Viride. We will probably be on the same orbit, and we'll cover the need of a mission, institutional mission that gives lower GSD and a higher performance in terms of SNR. It will have 3 missions: the foreground mission with the selected targets or regions, Italy and Europe. On-demand mission with several options depending on the target and on the desired product, and a background mission to image worldwide target. It will be a smart mission. We are thinking about cloud onboard detection to discard the download of specific cloud images. So after a long negotiation phase, we are starting the contracts for the phase up to the flight and to the commissioning in orbit. The launch is 2029. Thanks.
Thank you, Luigi. Next is Rob on the presentation of the mission status for SVG, I assume.
Yep, yes, definitely. All right, thank you so much. It's wonderful to be here in Europe. This is the home of spectroscopy, right? Joseph Fraunhofer, 1814, saw lines in the solar spectrum, and that led to answering the question is what is the composition of the solar atmosphere? That's extraordinary when you think about it. How are you going to know what the sun is today, let alone in the 1800s? So it is just a thorough pleasure to be here and to honor Europe for starting us on this path. And now we are moving forward internationally with cooperation. So I want to just quickly talk about the status of SPG VSWR. This is NASA's Global Mapping Imaging Spectrometer. It was called for, and what we have is a decadal survey that gives advice to NASA and the nation on where NASA should be going, and it did call for a global imaging spectrometer. As a high priority, it traced its priority to ecosystems, solid Earth, hydrology, climate, and weather, all of which we have contributions to make. Let's see if this works. All right. At the same time, those sort of science objectives, it's increasingly clear that we want applications, we want to offer services. So NASA is increasingly looking at Earth action, Earth science to action, and we're clear on many connections. When you measure a spectrum, you can get products with units and uncertainties to address applications, whether it's water management, ecosystem conservation, water resources, mineral resources, coral reefs. And so we're working in those directions again and cooperating across the international domain. Just to give you an idea, we are moving very quickly in development of the instrument. Now, the launch date is sitting out a little bit later than we'd like, but we know how to build this instrument right now based on emit, and this is an emit type spectrometer. I wanted to give you an idea. We're, again, moving very quickly. These are some of the components that are in-house right now as we move towards a PDR for the instrument core on Valentine's Day, February 14th, 2025. And then we'll have another important review on the U.S. tax day on the 15th of April for those of you who worry about U.S. taxes. I can remember those dates. Thank goodness they're picked for other dates that are important to us. I also want to get, this is very hot off the press. This is the first SPG VSWR grading. They're the biggest gratings we've ever fabricated at JPL. This was written in the last month on the left. And on the right, this is Avarice 5, which we're using to reduce risk and learn new alignment techniques. And this is alignment data I got yesterday from the clocking of the grading. Avarice 5 has a beautiful grading with some new innovations. And this is about the best alignment we've ever done in terms of getting all the wavelengths coming from the same location. So this is that keystone requirement. And we're now way, way under 5%. And so it's a beautiful result. I'd like to show results with the spectrometers. Moving quickly to the end, again, we're moving forward, cooperating globally with SPG VSWR, contributing to this global constellation, partnership and synergy with CHIME, of course. But we view this as a a new opportunity to look at the entire Earth system. Each of our spectra contains signals from the atmosphere and all elements of the Earth system, depending where we're looking. And with that, we can jump forward with both new science and new applications and close critical knowledge gaps. And I'll stop there. Thank you. Oh.
Okay, so now
Yes.
we have the presentation of CHIME mission status. So please, gents.
Yes. I use the microphone because I use it afterwards. So this is the last presentation before we go to the question and answer session. And with this presentation, I want to thank you all of you, because you really pushed this mission forward. We started with the mission expert group. I see some known faces in the audience who pushed in 2017 with us to go ahead. And it's your work which is presented, and we as a project team with Marco, Antonio is here, we are just representing all the efforts you have done so far. There are 3 posters here around where we go into the details on the mission analysis, on the campaign, and on the end-to-end simulator. Everything is there, can be discussed in these days. We started in 2017 with the expansion program. CHIME was one of those, and we have basically one slide here covering all the CHIME essential parts in brief. The key mission feature is it's carbon mapping, revisit time. We go down to 11 days with 2 satellites, the 12-hour maximum timeless, and we focus on higher radiometric accuracy and image quality. It's essential for that, for these kind of type of missions. Launch readiness in 2028, so we are just before, with the instrument already in the CDR, so the kickoff is basically next Monday, and we are producing already hardware, even flight hardware, in order to move forwards. Products are under development with partners. I would like to highlight here specifically the slide on the end-to-end simulator, where a lot of additional features are. By the way, there is another poster for the constellation aspect with SPG by Antonio. He presented this during the TIM workshop at SPG in Washington. Then focus on international collaboration. That's now. We are doing this. So we are coming together. We ask you, what can we do? And we try to implement. We discuss regular meetings with our colleagues at NASA, JPL, but also with DLR, with RZ and others. This is basically the 3 minutes I want to give you, and with each workshop, we're giving another update on that. Thank you very much. So what we have planned now is we have 2 online questions. No, they don't have it. They have it. No, they don't have it. Okay, Marco is bringing you the questions. One moment, don't leave. So, please use the QR code in order to, because we need to wake you up for this question and answer discussion, because you had now 14 presentations, and please, yes, I see that you already picking up this QR code, and try to answer, and we will live see how the answers develop. It needs a bit of activity on your side. Yes. Does it work? Because of the responses. So we are 100, 180, yeah, 180, 180 in the order. So we are now at 50%. Please, we need a bit of action here. Yes. Okay. Okay. So I want to see at least 120. We're coming there. And then we stop and we have another question. So for those who are trained, they're used to this, how does it work? So next time we have more than 120. Please, next question. Huh? Are they all answers to both? Okay, sorry, I hadn't seen this. Okay, then to look to you.
Okay, so let's see the first answers. So let's go back, please. So we have 125 responses, and we have, I would say, as expected, almost a 60% of weekly desired observation. 31% daily, I think that's a bit challenging. And 80% it's monthly. So, okay. In my opinion, there is a very large percentage of you that requested the daily observation. So it's nice to hear that. And then, which is the main factor limiting your use of imaging spectroscopy? The data volume, that is a surprise for me. The data volume is a limiting factor. The radiometric noise, well, I can see. The spectral noise, 21%. Can we expand the 24% of others? No? Okay. So could you please intervene? So what is your limiting factor to use imaging spectroscopy? Someone of the 24%.
Yes,
raise your hand, yeah.
Raise your hand. Where's the hand? Ah, there's a hand.
Hello, thank you very much. For me, the most considered thing to use hyperspectral is spatial resolution. So 30 meters by 30 meters, it's quite big for mineralogy analysis and all that. So yeah, that's for me.
Okay.
Yeah, this is Patrick Hoss at Humboldt University, and actually it was the first question. It's about the temporal resolution. If you look into vegetation, the effective resolution that you need is usually not met by hyperspectral data that we have today.
Okay. Hello, Matti Matos from VTT Finland. So the real issue is the availability. There is no regularly and reliably available data there, but of course, spatial resolution should try to go down to 10 meters or so. So actually, croplands and urban areas depend on that quite heavily.
It's open. Thanks. Similar to what Patrick mentioned, trying to pull together a synthetic time series of data across different instruments is still challenging because inconsistencies in the way data is processed, delivered, units, access. That if the efforts to harmonize should make that a lot easier.
Okay, I think this was nice. It's good to hear those things. They make sense. We can take note of them. One thing we mentioned, we went through 14 talks, and we didn't have questions after each one. I'm wondering if there are questions in the audience. Now we have a little bit of time that we could ask to the individual speakers. I see a question here.
I would like to ask to the PACE mission, which is the observing strategy. I don't know if I lost the information or...
The observing strategy?
Yes, so how do you select what you're going to observe? What is your...
We never turn off. It's the ocean color instrument in particular, a super wide swath, and so it is collecting, frankly, daily global coverage. So we only don't collect data on the dark side of the Earth.
Okay, thank you very much.
You bet.
There's a way to achieve daily, but you have to sacrifice one of those other parameters. Okay, other questions for the speakers?
For the first presentation we saw, I would like to ask to the presenter, what is the role, in his opinion, of the Earth observation missions, considering the development of commercial missions, and how the spectral accuracy of commercial missions has to be taken into account for the applications that will be developed from that?
I try to answer, then I ask also Jens to help me. So are two complementary roles. The mission, let's say the big mission, institutional mission, are the top performance reference mission that can be used for cross-calibration, for setting, let's say, the validation of data that need to be achieved for some scientific purposes, climate change, for example. The commercial are looking to the good enough economy. So they are not looking for the top performance, they are looking for what is enough in terms of cost and performance to win the use case. That can be governmental, or can be scientific in some cases, or commercial. And then there is also a matter of, let's say, revisit time. They typically tend to give, let's say, quite high revisit time. So I'm a bit surprised by the revisit time of 1 week. I was thinking that we were going in the direction of one daily revisit, which is actually what the commercial mission are trying to get. I don't know if it sounds
good. Just as a note on that, sorry, on this revisit thing, because the question was about effective revisit time. So after filtering for cloud cover, which I think you almost need daily to achieve a weekly effective revisit time. So I think maybe there's this thing that...
At the end, you are sampling a process which is monthly in terms of dynamics. To sample it effectively and shadowing it. Everything is faster than half a month.
Well, just wanted to follow up on Giuseppe. Of course, I will be preaching the truth again, but the role of the agencies, more and more there will be quantitative products out of the commercial activities with some legal commitments to it. And of course, when that time comes, especially if we are measuring the CO2 emissions, for instance, in the frames of international agreements, but also for commercial applications, the certification of the products will be essential. And that's where we want to play and place TRUCE and the other CITSAT satellites, of which the costs are so big that at the moment they are borne by public agencies.
Yeah, a question for all the missions, actually. I'd like to know which ones have a requirement on the second derivative of bottom of atmosphere reflectance. The point is that if imaging spectroscopy has added value over multispectral imagery, then there needs to be some requirement on the accuracy of the spectral anomalies, the spectral curvature or the second derivative. Otherwise, we just have a multispectral sensor with a lot of bands. So who has a requirement on second derivative of reflectance?
I think we might use a different term, but there are specs on the detailed spectral requirements, the response functions, the out of field with each wavelength. So we get at the information that constrains how the second derivative will play. And I agree with you 100%. If we don't have the high fidelity, which is another catch-all term, of really excellent spectroscopy, so we can see the subtle second and third order chemical bond interactions, we can't get at some of the value that's there. And so maybe when we talk about harmonization, how we would want to specify that so that's transparent to the users in terms of how we've spec'd that fidelity to understand whether they should expect to be able to see those fine spectral signatures, those small shifts from nitrogen compounds, et cetera, the lignins. Those are really subtle signatures. And then, of course, in the aquatic environment, the same is true. So I think that's a great question, and we should build on how do we characterize our instruments so that the user can see whether they can expect that level of fidelity to get at those more subtle signatures, which I think is the full power of spectroscopy.
Okay, I look forward to that.
That's my answer for emit and SPG.
And indeed, I just want to underline it's crucially important that we measure the pure spectrum we are looking at to make it to very simple terms. When we have a spectral band, we don't want to have out-of-band spectral responses. This is what we, or in case we have them, we need to communicate those to the outside world. And what you most probably see is maybe from a linear filter, they are prone to have out of spectrum responses, so that they will harm your algorithm and your retrieval.
It's a question for not specific to anyone, but before with the presentation for the NMAP in the collaboration with other missions, it was mentioned that there are correlation algorithms for different missions. So data from one mission can be transposed to data for another mission. How would you set the standard to which mission would you adopt as a standard, and on what basis?
I mean, that's a conversation for this workshop, and we want your input and feedback on that, in the sense that each instrument measures different things with their own characterization. And I don't know, we can force one to match another, but we can report them all accurately. And my evaluation of harmonization is they each produce the same product with uncertainties. Do those parameters overlap within their uncertainties? If we've done that, then we were on the right track. But they were all going to have slightly different characteristics, and we can't just force them, because then we'll lose that fidelity, which is the second derivative quality that we need for those subtle spectral signatures.
Another answer could be whenever it's possible to cross-validate different data sources. So I really like the activity you have seen for the NMAP and Prisma cross-calibration with the same target. And that would be a good example.
Okay, I want to ask a question in EMIT mission. We saw a very beautiful mineral map, and I'm very impressed with this result. Can you provide us the accuracy of this product, or how you do the validation and all the verification?
Yeah, we do validation at each product level using in situ data. So those validation activities take place for each of the products. And then in addition to the quantity that's reported, we also provide uncertainties for those quantities as well. And those are distributed with the data and can be downloaded from the public archive.
Perfect. Thank you very much for the answer. So do you have then approximately accuracy, the range, it's above the 50% of accuracy or something?
Yeah, that sort of characterization is an ongoing effort. It's very easy to propagate forward the parts of the uncertainty that we can calculate from first principles, the radiometric uncertainty and certain atmospheric uncertainties. Systematic uncertainties are far more difficult to deal with, and the activity of understanding and quantifying those systematic uncertainties is really the science that moves us forward in terms of measurement accuracy.
Okay, thank you very much.
So maybe the final question for one of the missions, Carsten.
Yes, thank you. I may have missed it in these 14 presentations, but it seems to me that we are in a good situation now with NMAP and PRISMA and on the ISS. And we have new missions coming toward the end of the decade. And NMAP and PRISMA seem to have reached their nominal lifetime or reaching it pretty soon. Is there a certain risk that we will be out of, or that we do not have a hyperspectral public sensor in space in, let's say, the second half of this decade? And how do we prepare in case?
Okay, so maybe, yeah, I'll take the word. So we are very happy because we were, so the orbit injection for MMAP was so good that we potentially doubled the lifetime of the mission. So we are already starting preparing for the mission extension, and we definitely look forward to cover at least the timeline until time will be fine. Finger crossed.
I will reply for PRISMA. PRISMA has entered the extended mission lifetime. PRISMA launched in 2019 with 5 years of life. So there is a risk, I agree with you, but I hope there will be enough lifetime to guarantee the data continuity.
Yeah, in regard to EMIT, we're in an extended mission, and we have a location on the space station to the end of the life of the space station. So this is all contingent upon the instrument continuing to work. There's always the risk, but right now I think we're in as good a position as we've absolutely ever been. And looking to the future, it gets even better with SPG, CHIME, PRISMA second generation, and the other missions we've spoken about here.
Let's not forget IRIDA. We will have in 2026 the launch of the first hyperspectral satellites. So will be some good news.
So I guess we're in this last section. I guess the question is from you, are there other things we can be doing in regard to the missions that we're trying to represent to make the data, the results, the products, the algorithms? David talked about how we're trying to make sure the algorithms are open source. What are your suggestions, in addition to some great suggestions we've had already? I particularly like the second derivative and the question of how do we know that the spectra are really worth working with? Do they have the quality to justify using them as true spectra? So I'll just open up the question. Yeah. Request.
So I learned about this conference a little bit late, but I am the vice chair of the IEEE 4001 Standard Development Group. And I think that this standard, which is going on public ballot these days and will come out hopefully in the winter, will be helpful for the community to come together and agree on how to describe the properties of even space missions, even though it has a sort of commercial slant to it in its first version. But I think this is something that we will all have an interest in building on in new versions to come. And if anyone wants to discuss standard, I'm happy to talk about that for as long as you like.
Thank you for that.
Other requests or comments for the missions we've talked about? There's a question up here.
Hi, Peter de Vries from NPL.
And it's been really nice to hear already uncertainties being mentioned and the importance of them in cross-calibration and so on. But I think one thing that would also be a very useful addition is some more characterization of the error correlation information. Because specifically, for example, with cross-calibration, we are combining multiple measurements. And so to do the uncertainties correctly, we need that information to do it. And often currently in the characterization of the instruments, I think sometimes that is a bit lacking, that detailed characterization, and it's often I would say it's often not in the requirements. So of course, industry doesn't do it because they're not required to do it, but it's something that in the future would be really nice to see added more of.
David thought a lot about this along with Phil and others, but I think it's a really important question.
Yeah, I agree 100%. It's the spectrally correlated errors that are often most detrimental to most algorithms, and we can definitely do a better job of characterizing them. We're also thinking about how they can be distributed in a way that doesn't explode our data volume with a covariance matrix for each pixel. So this is an area of active ongoing research, and I think an important dialogue for this workshop here.
Just want to mention that also on Chime side, and actually with some colleagues of yours, we are really starting digging into that and trying to come up with a radiometric uncertainty at level 1B, which is the most useful also for then later propagation in the higher level products, and in the end also future reprocessing and bringing these missions together. So we need your inputs to understand what is critical, but we're already having internal conversation and thoughts since quite a while. So it's good to have you here. It's a good time to nail any possible point which are uncertain.
Thanks. Was hesitant to ask this question because I'm not sure how to best formulate it, but I'll give it a go. Just have to talk closer. There was some discussion earlier about multi-angular looks, the options to point and tilt. I'm wondering if with the international collaborations that we have and will have going forward, and some of those having tilting and pointing capability, if there's an effort or an interest in looking at exploring BRDF or multi-angular effects in spectroscopy data in a very specific or coordinated way with those opportunities in the future.
So I will answer from the Prisma second generation side. Yes, there is the interest on the BDRF for the hyperspectral response from different angles. And we will have some specific requirements for that. We will have a stereo and 3 stereo image capability. So we will have the capability of acquire from 3 different angles.
And, oh yeah.
So the SPEX1 and HARP2 instruments flying on PACE are multi-angular. The SPEX1 is fairly hyperspectral as well too. So there are some ongoing projects specifically designed related to BRDF, if that's of interest.
And just to complement, I think on the Chime SBG concepts, I mean, there is always a trade-off between guaranteeing a quasi-nadir carpet mapping observations and being able, on the other hand, to sample, let's say, different, I was looking for you, couldn't find, and sampling, let's say, a variety of angles over the same target. So I think that in both Chime and SBG concepts, we try to maximize the repeatability of our measurements over time. But within the swath, we will have, despite being quasi-nadir, we will have this variability. So it's not a problem that we can ignore, and we are not ignoring that. And also, we are having some in the Chime level 2 developments, for example. I can speak for that. We do allocate some resources to try to make one step further compared to what has already been done for multispectral Sentinel-2 and Lancer.
Yeah, I think it's an important question. I think part of the information we want to provide with all our spectra is what exactly was the observation angle and what exactly was the illumination angle, because I think this is going to fall on the algorithms. We can report what was observed, but the algorithms are going to have to get more sophisticated to deal with the fact that they have a wide range. Even when we're quasi-nadir, right, we're going through the seasons, illumination angles are changing, and we do have a swath, so those angles. But I think what we can do is provide the information so that when those algorithms advance in handling BRFs, they have the information they need to take advantage of it. So that's basically the illumination and the observation for every single spectrum.
Okay, we have here a question from Giuseppe actually to the audience. And please, Giuseppe.
Now, I was curious because as we have seen in our database, there is, I'll say, a lot of capability or availability of data, seems, at least theoretically, and in particular from commercial mission and instruments. So I was curious who of you is using commercial data or public data? Can you please raise the hand if you are using commercial data in any way? So we have a huge availability and in this audience, a very low use of it.
There were 5 to 10, and we should follow up. And it'd be interesting to understand what the barriers to entry is, what your experiences are, because we certainly want to have everyone be successful moving forward.
Yeah, please, during the coffee break, talk to Giuseppe. Because it's a number of 10, I think he's able to count for it. There's another question.
Thanks. Yeah, that's an open question to everybody. I was reflecting on what I'm seeing on screen on the left-hand side. The data volume is an issue. I come from the hyperspectral infrared world where I worked 20 years and we were dealing with 8,000 or even 17,000 channels for the next generation. And one way around the data volume issue was using principal component analysis to maintain the entirety of the information instead of subsetting the channels and distributing that to those who couldn't afford the data volume. And so I was wondering if the principal component analysis is now part of this community, if this is being explored to compress. One other advantage beyond the compression is actually to discriminate between what belongs to geophysical signal and what belongs to instrument artifacts. And there has been some work in the infrared done, which I think would be relevant here.
So just certainly we're familiar with principal components. One challenge is that those second derivative signals that contain the subtle things like nitrogen and some of the water qualities are in the high principal components. They get shunted up there when you do a principal component in our assessment. So it's tricky. You need to be careful. Yes, you can compress the data with principal components, but maybe you're also washing away some of that subtle critical signature for the harder questions that we want to tackle. But it's an area of exploration. I'll let others comment as well.
Okay, we follow. I mean, this is seeding question for all the discussions we have over the following days. So we see that you are engaged from the number of questions. Please continue with, and also look for answers and report them in the different breakout sessions coming tomorrow and the day after in order to conclude for this workshop. I think this is very important. For this, I think we close the session. Thank you very much.
All the speakers.
Yeah, and we have now some time before the lunch break for the first poster session. This again is just entirely left up to you in the way you want to interact with people. We are here in this room for an hour and have a look at the posters because I think there is a great selection, and then try and engage with people as in the way, shape, or form that you prefer. Okay, thank you very much. Just I forgot one thing. For lunch, we will. Yeah, I see you have a question. I'll give you the. We will try to open the lights in the back. Thanks. And No, the only thing for the lunch break, again, we will move basically together around 1 from this room. If you have not collected your badge with the pink lanyard, please do that here on this side of the stage, because it's very important. Otherwise, the security will stop you at some point going around, okay? And Sabrina?
And for the speaker of the next session, you can approach the speaker ready area to upload your presentation. Thank you.
Yeah, thank you. That's all. Okay, so it's time to restart, and I'm very pleased to introduce the next the chairs of the next session. So yeah, please take a seat. We have Sabine Chabrilla from GFZ Potsdam, and then Kevin Alonso from Esrin, and Philip Broderick from NASA JPL. And I'll let you the floor. And again, just a very quick note. I think we started on a very positive note this morning. And also thank you for sticking to the time. Let's keep that so that we make sure that we have even more time in the afternoon for interactive discussions as we did this morning. Thanks. Please.
Thank you, everyone. We will start the third session, Instrument Agnostic Algorithms. And the first presenter is Jochen Ferrels from University of Valencia. And he will be presenting the time end-to-end level 2 vegetation processor updates and upcoming initiatives.
Sorry, I've seen some issues with the clicker this morning. It just has a slight delay, so be patient when clicking. Thank you.
Yes, thanks, Marco, and thanks, everyone. And I want to update you about the process on the Chima Level 2B vegetation processor. That was done with many people, especially I want to thank Jose Luis, he's in the room here, who did most of the work. And moving directly to the outline, I have no time to go through it, but I want to point out a few novelties that we will present here. Above all, novelties in the Level 2B processor, and also how to deal with agnostic or generic functioning of the processor. This project is part of the end-to-end, which basically is building the building blocks of the processor of all the Chime data, eventually until Level 2 high-level products such as vegetation products. We are responsible for the so-called priority vegetation products, which are leaf area index, nitrogen, leaf mass area, but of course, more products can be developed. So at the end, we have a whole suite of vegetation products that can be developed from Chime. What would be the ideal algorithms for us? Of course, when you move towards operational processing, they have to be generic applicable, both in space and time. They have to be fast, they have to be with uncertainties, and above all, they need to be accurate. For that, for us, we felt like that the so-called hybrid methods are best satisfying our needs. And hybrid methods are those methods which is a combination of RTM data that you use for training so-called machine learning algorithms, MLRLs. But on the other hand, when you move towards machine learning data, the main problem is the redundancy, both redundancy in the spectral domain, that can be easily solved with PCA reduction. Of course, there is always a trade-off how many PCAs at the end for us in order to extract these subtle information such as nitrogen content. About 20 PCAs typically works well. On the other hand, there's also redundancy in simulated data. With RTMs, you can simulate millions of samples, but not all of them, they actually add to the accuracy of the model. So we apply methods to intelligently select the most useful simulations that adds to the accuracy of the models. Then also there's a question of the machine learning algorithms. For us, we felt that the Gaussian processes is the benchmark algorithm, as that's an algorithm that provides by default uncertainty. We feel that you cannot apply any other algorithm if it doesn't apply uncertainty, because without uncertainties, you don't know anything about the performance of your algorithm. Nevertheless, there are other algorithms that also are interesting, and we also included those. Talking a bit about uncertainty, in fact, there are two types of uncertainties. No, there's on one hand the aleatoric uncertainty, which is always there. It's due to probabilistic variability, and that's uncertainty that is being propagated from one product to another product and so on. That is always there. We cannot do anything with it. On the other hand, there's also epistemic uncertainty, and that's uncertainty that comes from the model itself. And there you can improve by retraining. So until that uncertainty is, you try to have it as low as possible. Epistemic uncertainty you can calculate in various ways. With Gaussian processes, that's in the Bayesian way, but also you can think of random forests, where you have ensemble of trees, or bootstrapping methods, also where you have ensemble of models. So at the end, we can calculate epistemic uncertainty within the processor. Coming to the processor, the novelties now is that apart from the Gaussian processes as a benchmark algorithm, now we have by default 4 machine learning algorithms implemented. First, we had that they were always there, but that just one of those models, depending on if it's best performing, was included. But now we have for all the variables, all these models included. So if you prefer to use neural networks, you can select a neural network, so Gaussian process and so on. Another interesting feature is these so-called optional features, which is smoothing, finding peaks, and removing bands. And we feel that it's very useful. We had to develop that because it can always happen that a band is corrupt or is shifting so what. So we had to come up with interpolation techniques to fill up missing bands relative to your trained model. And then also we have finding peaks and removing bands. But all these features cause that actually now the processor can process any type of hyperspectral data. So we can, it works for CHIME, but it just works as well for Prisma, NMAP, or any other image. So this is the workflow. Eventually, we evaluated these algorithms. We evaluated that for with experimental data, synthetic data with all kinds of vegetation configurations, and now finally to real imagery. The experimental results are very good for at the canopy scale, not so for the leaf scale, but for us, that doesn't really matter because what matters is that we have the workflow developed and we can continue to keep on improving the training until eventually, finally, these models are good enough to be part of the end-to-end. This is an overview of the synthetic scene. So it provides also the uncertainties. You can see some models do well, others do maybe less well. But then you can apply it just as well to the Prisma. It immediately processes you out to these vegetation variables together with the uncertainties, or to NMAP, just the same procedure. It's all automated. Or if you wish, also for airborne data, for highplant, for instance, now also all these traits are being processed in an automated way. Finally, we receive often a message from ESA and others that we should move towards open source. So far, this has been developed in MATLAB and then compiled in C++, so that's into the internet. This is for the first time now that we release also a Python alternative, and it appears it works way faster. It uses less memory. Only so far, only the GPR models have been included. But the nice thing of this Python package also that we will release is that it can also process in cloud computing. So our models on Sentinel-2, Sentinel-3 are already they are operative. As soon as ESA will provide or anyone will provide hyperspectral data into the cloud in Google Earth Engine or OpenAO, we are ready to process that into our vegetation traits. And with this, I would like to conclude. ESA also asked me a few questions about how agnostic our processor is, especially with machine learning. Is there a need for retraining? And here, our answer is that actually the models should never be touched. It's rather the image processing where the work lies. So we have this resampling in a way that in this way, actually, the algorithm is agnostic for any kind of hyperspectral image. That was my presentation. Thanks a lot.
Yes, we're going to wait and do questions and discussion at the end. We'll call you back up. So next, we're excited to have Ray Coakley to talk a little bit about comparisons of reflectance and mineral identification.
Thank you. Good afternoon, everyone. I've got 31 slides in 7 minutes, so hopefully this clicker works well for me. What's motivating my involvement with this work and looking at all these different sensors at Cooperite, Nevada for mineral mapping? The USGS has a big project called Earth Mapping Resources Initiative. It's a $350 million+ effort to collect new geophysical data for geologic understanding of the US. That includes airborne geophysics, geologic mapping, geochemical sampling, but also imaging spectroscopy, which came on in just a few years ago. And we've done a lot of work to collect imaging spectroscopy data for the nation in those 2 years. The first thing that we did with the Earth Mapping Resources Initiative was look at the data we have available for understanding geologic resources in the US, in particular critical mineral resources. Critical minerals are those minerals that are important for the nation's economy, for national security. They're the elements that are in your cell phones, in your wind turbines, in your green energy technology. So it's really important to know where these are distributed. What we found, though, is there's not a lot of great high-quality geophysical data for the US, so we needed to collect more. So that's the effort we're doing in partnership with NASA to get airborne imaging spectroscopy data for the Western US. So as part of that, we're looking at collecting hundreds and hundreds of flight strips. We need to calibrate and validate all those data. And so we're doing that in the Western US, and we're going to apply that also to these spaceborne data sets at Cooperite here. I'll show you those results. Skip through this, don't have time to really get into the MICA method, except that it's a spectral feature comparison method like tetracorder being used for the emit mineral mapping and other systems that are out there. So what we found with the data being collected for Earth MRI in partnership with NASA is that our benchmark validation data set in 1995 collected with Avers Classic, that's the image on the left there, compares very well with the data we've collected from Avers Classic in 23 and 24. We even see improvements in the mapping. We get better discriminations where the minerals are weaker. We have better atmospheric correction methods. So our benchmark data set really for comparing the satellite images is that data set in the middle. And we've validated that result with 26 different validation points of varying mineralogy throughout that area. So we're going to compare the mineral maps from that ground calibrated, very good airborne data set to results from these sensors. First thing we did was run through the different levels of atmospheric correction for those. You can see those listed here. A lot of different techniques and a lot of variation in the spectral and spatial characteristics for these data sets. Don't have time to really get into all the details, but you're all aware of them. Then we looked at the geolocation errors in the data because we want to try to validate these with the field data, so we need to have the pixels aligned with the field validation sites. So before we did any refinement, we saw errors around one of them, Nmap was really good under 1 pixel of GSD error, but some of them were quite large. So we then forced those to match a Landsat image base. And we brought those errors down to less than 1 pixel of GSD. So now we know that if we try to compare the field data that has a decent location, we can compare hopefully 1-to-1. And we'll just skip past that. Part of what we do is make evaluate the reflectance data for a known calibration site at Stonewall Playa. So here you'll see plots of data from the satellite in the colored lines compared to the field data in the black line. And you can see that there's a lot of good agreement in these, but there are some places where you see residual atmospheric features that are going to potentially interfere with our mineral detection. And you see that for all the data sets. They're in various places, and particularly though they tend to always be in the 2.3 micron range and longer wavelengths and the short wavelength range. So those are places to really key in on and understand what residuals you have in the data and how they might affect your algorithm. Some have greater residuals than others. We see a lot of residuals in Prisma. This is HISUI data. It's been empirical line corrected, so we see less of those effects in there. And this is GALFEN 5 AHSI data. So you can see there's quite a lot of variation there. So we expect that all to affect the mineral mapping. And when we compare images, we expect to see that in there. For AHSI, we didn't ground calibrate this data because there were saturation effects in the bright pixels. You can see the spikes here that show that. So we weren't able to look at a ground calibration versus a level 2 reflectance product for those. So finally, getting to the comparisons, we have here Avarice Classic on the left. We have the ground calibrated Nmap data, mineral map in the middle, and then the Revel 2 reflectance product. You can see on a whole, there's really great comparisons in the mapped minerals. The colored pixels match pretty well between them all. You can see some variations though, so also with emit. Again, good correspondence, but if you notice in that black area where there was no detection in the airborne and the ground calibrated result, we're getting some residual features in there in that 2.3 micron region that are causing false positive identifications of minerals. So we see these very good comparisons for emit and Nmap for the level 2 product and the ground calibrated product. For Prisma, a little less good result with the level 2. There's some big residuals in there that interfere with good mineral mapping for those. And for HYPERSPECTRAL with the empirical line correction, it actually did okay, but we didn't really improve much with the ground calibration, so that there's a little bit of a cost to doing that. AHSI data, not a great result in comparison to our reference data, and no ability to ground calibrate that. Don't have time to get into all the subtleties of some of the mineral wavelength mapping, but any of those orange areas you saw mapped before, that was the mineral muscovite or the mineral illite. Well, within each one of those mineral classes, every pixel could have some variation in the wavelength position, so that's important to know. And we do see variations across these 3 data sets. AHSI data wasn't as good as reproducing the Avarice data as the other data sets. So I think maybe the summary image to leave you on would be, let's see if it's this one here. In terms of the accuracy assessment across these different systems, we saw graded results, better results when we ground calibrated and grouped the mineral classes compared to when we tried to use exactly every one of the 142 minerals and compare those across the data sets to see if they matched exactly the right one. And the accuracies range from 50 to 60% when you don't have ground calibrated data and you're looking at the strict classes, to 100 to 90% for the airborne systems when you do group them and you do ground calibrate. So it's kind of a mixed bag. Ground calibration and grouping classes really help. So we should do that when we're looking, when we can. And when we're thinking about comparing Nmap to emit, we'll probably want to do grouped classes, for example, and compare those grouped classes rather than the strict classes. So final thoughts, we should develop more of these geologic proving grounds like Cuprite. There's an IEEE GRSS GSIS working group that I lead that is doing this. Chris Hecker here is part of that as well. So we need, many of these sites around the world with the diverse geology. And as I mentioned, I think we'll get a lot more improvement in our results if we improve reflectance at wavelengths 2.3 micron and longer. And then finally, is this an agnostic algorithm? I'd say yes, it is. We can certainly apply it across all these data sets. That is, if the sensors are well calibrated, characterized, the reflectance data are relatively free from artifacts, and the spectral absorption features are pretty strong, then yes, they can be pretty sensor agnostic. So thank you.
Yeah, thank you, Ray. Then I will introduce the next speaker, which is Saed Azadzadeh. He's from the GFZ, the German Research Center for Geoscience in Potsdam.
Good afternoon, everyone. Hopefully, Ray provided the background for this study, so I will skip the motivation for doing so. But what I'm presenting here is to see how machine learning could regenerate the stuff that we could produce by mica, which Ray showed nicely in the previous talk. The sensors that we have studied, you already know, and we compared them from different aspects, but here is the stuff that I'm going to show you for mineral mapping using different machine learnings. I mean, we have used several other techniques also. Some of them were not performing well, so we are showing just the best ones. Doesn't work here. pointer, yeah. Anyway, you see that the like random forest support vector machine with the two different kernels, k-neighbors, extra trees, and unit deep learning method applied for the to the image over cuprite, and you see here the results, the maps, and the overall accuracy sorted there in the table. You see that despite our expectation, like the support vector machine is showing the best results and even outperforming the deep learning method. The same results we got from the short wave when we applied that technique, and this to the data from Nmap. Here you see I mean, different data sets have been used, but you see the example from Nmap here. Here are the results when it comes to sensor comparison. I mean, Ray showed all of this, but here again to highlight that Nmap was the best sensor, the best spaceborne sensor to have the results closest to the Mica when it comes to machine learning. In terms of the classification results, I mean, we had got different classes in the veneer, as you see on the left, and then also different classes, including some mixed classes in the short wave. See that the performances of the algorithm are not the same per mineral. Some minerals are used to be detected quite effectively, and some of them are not, specifically the mixed classes. For example, you see the calcite and monzmonite here are doing not doing well, because it is like a subjective definition. But I mean, generally speaking, for majority of the minerals that they have distinct absorption features, they are doing well when it comes to the classification. For the, I mean, the sensitivity to training, I mean, we had this, let's say, ideal training, and then we consider that 100%, and then we did just over several steps, we decreased that to 50%, 25, 10 and 5% to see how they react to the training data. And you see that the SVM in both visible and short wave, it keeps the good performance up to 25% or even 10% of the original training data, meaning that it is not as sensitive to the training compared to deep learning, for example, which is quite sensitive. And then it immediately drops when you reduce the training. This is the same for short wave range. You see that the performances drops for deep learning units as well as for random forest, but not for support vector machine with the polynomial kernel. This is the comparison between different sensors when we applied the standard reflectance data and then refined one from USGS. We could see that refining the reflectance, actually, it has got lots of effect on Mica algorithm, but for machine learning, it is not that much sensitive. You see that it improves the results, but still for Nmap, at least it's just at the same level. For other sensors, it improves the results a little bit, but not so much. Meaning that they are not very, very sensitive, at least the support vector machine, which is the selected one, not very sensitive to the quality of atmospheric correction. The same story for the short wave. Just to conclude, the polynomial, I mean support vector machine with polynomial kernel, we showed that it could regenerate results close to Mica. It is not very sensitive to the quality of atmospheric correction. Of course, it could improve that, but not that much sensitive. Also, it needs the least amount of training data to be trained. And also, I mean, generally speaking, machine learnings, we realize that they are very sensitive to mixed classes, and they have got difficulties in tagging them, maybe because they are subjectively defined in Mica. And the last thing, I mean, I haven't shown any 3D CNN results here, but we also did some testing with 3D convolutional neural networks, and we realized that they are not better than 1D. So one of the other conclusions that we had is that 1D CNN would be good enough for neural mapping, but still none of them could outperform support vector machine. So in just the message is that we don't need to go towards the more sophisticated methods. Just the support vector machine with a good kernel could satisfy this job. And then my last slide is just the other topic, CHYME, which Carl wanted me to show. And we are also doing some machine learning related work regarding kaolinite abundance mapping. And you see that we were able to estimate the areal abundances for kaolinite, volumetric, and areal, and then uncertainty using the machine learning method trained specifically for kaolinite. And that's it. Thank you.
Our next speaker was scheduled to be Jeff Dozier, who unfortunately has recently had an accident. If you know Jeff, you know there's nowhere he'd rather be than with his friends and colleagues here with you today. We wish him a speedy recovery. Fortunately, Nicholas Bond has agreed to step in. Take it away, Nicholas.
Thanks, Phil. Yeah, I just do hear what Jeff would have wanted us to do, just continue the snow spectroscopy. So we wish him all the best and a speedy recovery. It's really sad that he could not join us this week, but I just take it over and give an insight into snow properties and what we're planning to do in terms of retrievals and algorithms for upcoming missions like SPG and CHYME. What's the path towards these missions and what do we deal with in the snow spectroscopy world here? So what is snow actually? So snow is a mixture of air and ice particles on the surface, and the difficulties about snow is actually that it could have many different shapes and shape distributions, size distributions, and although if you look at snow, you would think it's like a homogeneous surface. It's like horizontal and flat. It's easy to do spectroscopy over snow. It's a bright surface, so you have a good amount of photons reaching the sensor, but actually it's more complicated. So you can see a lot of different structures here, like microscopic structures, and also if you look at the microstructures here on the snow surface with all these roughness, it's actually more complicated than we would think. So what has been done in the past was that people have been developing different forward model approaches. So there's the traditional Ruskin and Warren approach using delta Eddington mean scattering. Tom Painter used non-spherical snow grains. He heavily relied on disorder. That's what I'm doing too, actually. The Kokhanowski and Ziga approach, geometric optics, asymptotic rate transfer. You see there's a lot of different ways to do forward modeling of snow reflectance. And so it's really important to know what's available and to really select the appropriate approach here if we want to get the most accurate products finally. So we're basically, as every other focus area, we're following the decadal survey objectives as mentioned earlier this morning. And for snow, it's actually the hydrology part of the decadal survey. So we're looking at snow and glacier albedo. That's one of the most important objectives here. Parameters are snow ice coverage fraction, the surface reflectance, of course, and then we need the snow grain size to calculate the product we're finally interested in, which is the snow spectral broadband albedo. So this is coming from the decadal, and we're following these guidelines here. So as I said before, the snow albedo is really the quantity we're interested in, and there are many, many factors when this albedo gets darker, and actually the absorption increases. So as Jeff always used to arrange it, that we're actually not interested in the albedo, we're more interested in the absorption of snow, which is 1 minus the albedo. So if the albedo decreases, the absorption increases way, way more. So we're interested in the factors that actually darken the snow. For example, when grains get larger, or when snow is contaminated by light-absorbing particles. Also, when the snow is shallow or it's dark and visible, and the snow is shallow, snow water equivalent is smaller than 500 millimeters for larger grains. So it's usually a whole compound of different factors that increase the absorption and lower the albedo. So that's actually what we're interested in, and we need to get a good sense of how we want to actually retrieve that, and also the uncertainty margins we're looking at. So this is a very I would almost say like famous picture Jeff always used to show in his recent presentations. I think this was just taken right outside his almost backyard in Mammoth Mountain, Mammoth Lakes in the Sierras. So as you can see on this picture, on the left-hand side, the sun is actually, or you are facing the sun with your view. On the right-hand side, the sun is behind you. And what you would expect from snow rate transfer models like this sort is that the surface on the left-hand side should appear brighter because of the forward scattering. Actually, it does not, because we have all these so-called sun caps in the snow, which is surface roughness, which causes small subpixel or surface roughness shadowed areas, which cause the snow to appear darker, even if you look into the forward scattering direction. So this is really one of the challenges we need to face when considering all the algorithms we want to apply and the models, that snow does not actually always behave like the models think. So based on these findings, and in a different presentation, Jeff came up with some recommendations for how we should put the uncertainty requirements to our products. So we should, as I said before, we should look at the absorption, and we should specify that the sensor, also the data processing algorithm, should retrieve actually the square root of the effective rate of snow grains, as this is more linear compared to the absorption, and the error should be within 18%. The same accounts for the darkening of snow, so actually the difference between the estimated clean albedo and the actual albedo, which we usually integrate over wavelengths from 400 to 900 nanometers, because beyond that, these particles don't have any significant absorption effect. So we should retrieve this to within 12% RMS error. So these are guidelines Jeff put together based on a sensitivity study he did a few months ago. So we should try to at least consider those and try to follow those in concert with the decadal survey objectives. It still doesn't solve the problem of surface roughness. As I mentioned before, and as you've seen, rougher surfaces are darker, but also we need to still think about how we want to approach the atmospheric modeling strategies over snow, because over bright surfaces is really challenging, as aerosol retrievals are not as easy as for over darker surfaces. So what we can do, and I go to this through this really quickly here, so we can set up refined product error budgets for snow parameters in the view of upcoming SPG and CHIME missions, so we can look at our snow grain size error budget, absorption, and finally also the albedo. This needs to be refined with more comprehensive sensitivity studies, also including different illumination conditions and view conditions. So this is really important, but it's a good guideline to start with. We're doing some like basic preliminary studies looking at mainly emit products here. So this is an example from the Italian Alps. And you can see a kind of example workflow. We start with the direct reflectance factor. We go through spectral unmixing to get the fractional cover and the grain size. And then finally, we apply very simple equations to get to the Broadband albedo. So that's actually the final product most people are interested in. And this is an example pipeline where we're planning to follow these and refining this with updated algorithms and approaches. So to conclude here, one thing which Jeff and all others also pointed out very many times is that we need to retrieve albedo, including grain size, LOP characterization, and the fractional cover together. So we cannot do this like in a subsequent row of like approaches, but we just need to simultaneously solve for all of these to get the most accurate product out of it. Also, the properties get more accurate, the retrievals get more accurate if we include the effects of topography. However, if we do this, we need to make sure that the information we include is accurate. So it's, for example, the issue that digital elevation models have more or less errors associated with them. So if we don't include these errors, don't propagate them through, although we consider topography, actually introduce more errors than if we won't do it. Some next steps, this is just to let you know what we're planning to do in the SPG context. So we're putting a lot of emphasis on the open source development here, putting algorithms and ATBDs on GitHub, doing the preparation of calibration validation plans. CQ strategies are very important, data fusion, connection to Earth action application. So this is all part of the snow and hydrology focus area of SPG, which is, as I mentioned before, informed by all the work the community does, so including of course, Jeff Dozier's recommendations here. Also synergies with other NASA missions, for example, from the radar side, but also explore synergies between vSphere and thermal infrared. So this basically accounts for all the different focus areas. This is just the example for snow and ice, but you can do the same kind of slide for aquatics, terrestrial vegetation, and geology. Thanks so much.
Yeah, thank you, Niklas, for jumping in, and yeah, our best wishes to Jeff. So Biagio Di Moro will present the next talk, and we stay in the snow and ice.
Hello, everyone. The title of my presentation is Snow and Ice Surface Properties Derived from Imaging Spectroscopy Data. I will show some algorithm and sensor comparison. Okay, this is the aim and summary of my presentation. I will show some evaluation of level 1 and level 2 products from Prisma and Nmap for snow and ice in different places of the world, but the Alps and Antarctica and Greenland. I will show some sensor comparison for liquid water content detection in snow and some algorithm comparison for mineral dust concentration. I take the chance from Niklas' great presentation to skip the first part on the introduction. So I will show you directly some matchup comparison that we did for Prisma, level 1 and level 2D in the Alps. We made use of a flat areas, snow-covered areas. This is Plateau Rosat, is in the European Alps. In this study, we made use of 2 alpine sites and 1 Antarctic site. And for flat condition, both level 1 and level 2D behave quite well, and they have a mean absolute difference lower than 5%. Then when we add a complex terrain, the situation gets more complicated, and the error rises. We did similar analysis for Nmap level 2A. In this case, we did also for level 1, but I'm showing only the reflectance data for the Greenland ice sheet, Antarctica, and the Alps. Also, in this case, the matchup is quite good for flat terrains. And after that, we decide to take into account the topography, since mountains are not flat, and the impact of topography is quite high in snow and ice spectroscopy, but in particular for snow. So we see there is a great dependence on slope and aspect variable, in particular in wavelengths that we use for retrieving impurities. This is in the visible part of the spectrum. We developed this new product from Prisma. We called it Level 2D SHIA, which is the name of the ASI project that supported this analysis, where we start from level 1 Prisma. We go into the Arosix script in order to get a better positioning of the image, of the Prisma image. Then we use ATCOR for the atmospheric correction, and we use the Picard modeling to correct the slope and aspect effect on snow reflectance. So I'm showing some results for the dust concentration in first place. We made a comparison between 3 methods. This is the first one. In the Alps, we had 3 major dust events this year. You can see in the lower figure that at the end in July, we have the snow heavily polluted with dust at the surface. And we had this Prisma image in July, and we applied the first method. It is based on a simple ratio between logarithm. This is the impurity index. And we came up with this concentration of dust at the surface. The second method of increasing complexity is a machine learning method based on the KNNR. To estimate the dust concentration, we made use of biosneaker simulation that accounts for the topography effect, and we get a good matchup between the simulation and Prisma spectra. And in this case, we estimate both jointly the grain size and the dust concentration. And the last method that we apply here is the Kokanowski method, is the asymptotic radiation transfer theory. In this case, we looked at a small area that does not account the complexity for the topographic effect for the moment. And the concentration comparison between these 3 methods are promising, so at least the average is comparable between these three methods. We are still waiting for data analysis of the dust concentration in snow to have a proper field validation of these three methods. The other parameter that I'm showing here is the liquid water content in snow. We developed this method based on this absorption feature here in a 1030 nanometer. When liquid water content increased, the absorption shift toward a shorter wavelength. So we exploited this thing here to build this snow superficial water index that is normalized for the dry snow. So it is independent from grain size and it's linearly correlated with the liquid water content in snow. So after that, we applied this method on Prisma image, and the results were reasonable. So we successfully estimated the liquid water content. Then we classified in like dry snow, melted snow, or very melted snow in this liquid water content classification. We have this paper from this year in remote sensing of environment with more detail on this story here. One other thing that we applied the same method to one Nmap scene during one campaign that we did in Cervinia in Western Alps this spring. The situation was very in the accumulation snow, so snow was very dry, but we managed to have a good matchup between field spectroscopy data. Oh, sorry. This is not working very well. The field spectroscopy data and the Nmap surface reflectance, and we compared our measured in the field liquid water content with what estimated from Nmap, and they are both lower than 3% that we can consider a dry snow that is acceptable for this kind of situation in the Alps. So this algorithm is promising also on the Nmap mission. So sorry. So this brings me to the conclusion of the presentation. I show some Prisma and Nmap matchup analysis with field data in the Alps and in polar areas, and the comparison is quite good for flat terrain. And when we have complex topography, we get higher errors. And we developed this novel custom level 2 geocoded Bohr reflectance product that also accounts for the slope and aspect correction. This is promising because we have to take into account, since we do the retrieval using the visible wavelengths, the reflectance in the visible wavelengths. So the liquid water content can be successfully retrieved from imaging spectroscopy data with 10 nanometer spectral resolution. That's why we consider this approach here to be instrument agnostic. This is very data not agnostic because we built it with field measurements of liquid water content and spectral reflectance in the field. So we must add more situation and hopefully include also the estimation of liquid water content in ice, which is way more interesting also for glacier ice in polar areas. Mineral dust concentration can be retrieved with these three methods, and they need to be evaluated with dust concentration. This is not an easy task, since the dust concentration is often not homogeneous over 3x3 pixel of Nmap or Prisma. So the validation effort is on the go at the moment. So that's all for me. I acknowledge the project that made this presentation possible. Thanks. Thank you. Now I would like to call our next presenter, Arthur van den Hoeke from Cuba Space, and he will be presenting us advances in deep learning spectral models for mission agnostic cloud detection.
So good afternoon, everyone. My name is Arthur. I'm a data scientist at Cuba Space. Glad to be here. So today I'm going to be talking about advances in deep learning spectral models for mission agnostic cloud detection. So before getting into the technical details, let's just step back for a second and try to understand what exactly we're trying to solve here. So over the last decade, we've seen big improvement and progress in satellite technology, so sensors, hardware, software, but also in ground network infrastructure. And those have introduced a a clear shift towards small, affordable, and disposable satellites. And that is especially true for hyperspectral data providers. They need to face very rapid disaster response, being able to monitor the environment, also security, surveillance, reconnaissance. All that needs to happen fast. And you have clashing objectives here, essentially. You need to be able to provide high spatial and spectral resolution images using limited bandwidth for downlink transmission and at small operational costs. So how do you solve that? And one way of doing that is to reduce the amount of data that you need to send down to Earth by processing it directly on board the satellite. So one obvious way of reducing the amount of data that you downlink is to filter it by the amount of cloud cover, right? So therefore we have two cloud detection models, one on board and one on ground. The onboard cloud detection model happens right after band alignment because it's a snapshot imager. And the second one happens after auto rectification on the ground. So those are two different models that I'm going to be talking about today. Yeah, so let's dive into it. If you think of the methodology now for onboard cloud detection, you might think of the golden standard of computer vision, so using transformer models, right? But they're extremely difficult to bring on board for several reasons. They're extremely data hungry. They're quite big, so they come in tens of millions of parameters. So they're tens to hundreds of megabytes in footprint, in memory footprint. So way above the uplink capacity. And the latency comes with it, right? They're quite slow. So this is why we went for a slight shift. So it's a light vision transformer with an enhanced self-attention mechanism that operates on visible and near-infrared bands only. It's very small, so it's maximum 1 million parameters. It has a very small latency, so we're talking about millisecond inference time. And it performs quite good because it's performing above 90% F1 score on binary classification because the on-ground model will be multi-class. So how did we train it? We used two different data sets openly available, Landsat 8 Biome that implements 4 different classes in the visible, near-infrared, and shortwave, and the combination with 95 Cloud, which is only cloud, no cloud in the visible and near-infrared. And we used very aggressive augmentations. That was actually the key to getting good generalization. And it performed actually quite well. So we got 90.28% F1 score on binary classification. And the surprising thing here is that when you compare it against more traditional methods that were handcrafted for a decade, basically, like function of mask, it was tailored for Landsat and Sentinel, we got way less false positives directly, so out of the blue. So it's unseen data and it's just performing very good. So that was a really good hint that it might actually work for different platforms, right? Now, if we move on, we benchmarked its latency on 2 different hardware systems. The first one for our first generation satellite it's a CPU, so it's using this image size of 384 over 4 bands. We got 5.43 seconds per image. And if you go to our second generation satellite, which will carry a GPU in 30-watt power mode, you can get up to 431 milliseconds per hyperfield 2 image. Sorry, that's a typo. So that's 4 megapixels. And now, if we release ourselves from these onboard constraints, we can talk about vision transformers now, actually. So we decided to go for a vision transformer on ground because we have bigger infrastructures, like I said. So we're using a 5.5 million parameter model. It's still very small. We didn't want to use too complex architectures. It's trained on the same data set, but this time it's 4 classes. So clear, thin, thick clouds, and the cloud shadow. And we're using the same augmentations as before. And now the trick here is that we're using this Landsat 8 Biome dataset to produce a first version of this trained vision transformer. And this transformer is going to predict cloud masks over a set of 600 Prisma images. And then we manually fine-tune those inference maps to get better quality cloud masks. And then we retrain the model, and then we do this over and over again. And we will actually see that this curated data set leads to very, very good performance for this small vision transformer. So this is actually an example of cloud annotations. So we really picked very tough images for Prisma. So you can see the cloud shadows in blue and also this interplay between thick clouds and thin clouds. So that's the type of data we're dealing with here. So it's pretty tough for it to learn. And you see the evolution of the model performance throughout the different training rounds. So we got from 92.78% F1 score all the way to 94.45. And you see, especially for cloud shadow, which was badly present in the Landsat 8 biome data set, that it really started to pop up in our inference masks throughout the fine-tuning rounds. And that's another example on Prisma imagery. So it's really working across sensors. Now you have this nice interplay against with thin clouds, thick clouds, and cloud shadows. So that was really nice to see as well. And that is actually a good surprise we got last week, is it works out of the box for Hyperfield 1 imagery as well. And this one is uncalibrated. So you can get thin and thick cloud information already on uncalibrated data. That's pretty much all I have to say today. So yeah, how much instrument agnostic are the current state-of-the-art algorithms? Well, if you look at FMAST, for instance, it's really handcrafted spectral indices that were made for Landsat and Sentinel. So here we're really one step further. And if you look at other data sets like CloudSense 12, they're adding all kind of different data modalities. So here we're really dealing with a minimalistic data set. And that is, I think, also the key to getting truly instrument agnostic models, is that you have to acknowledge the fact that data and models, they work hand in hand. So you have to not only choose a data set that is curated but accurately represents your learning problem, but you also have to choose a model that is complex enough to capture good image representations. Yeah, as I always like to say, an uncalibrated cloud remains a cloud, and it's your job to kind of tweak training data and models to make it learn. Thank you.
Next, we will have, we'll invite Leonard Anson to give us a talk on a comparative study on band alignment algorithms.
Hey, hello everyone. My name is Leonard Anson. I'm a data scientist at HYPERSPECTRAL, and today I will be talking about a band alignment benchmark that we have created. I just figured that I don't have a clicker. What is the reason that we need to perform band alignment in the first place? So HYPERSPECTRAL's hyperfield satellites are equipped with hyperspectral 2D snapshot imagers. That means that the images that we acquire are misaligned with respect to each other, regardless of the wavelength at which they are acquired. Therefore, alignment is required to properly align the hypercube that we acquire with the satellite, and in order to reconstruct the full spectrum for each pixel in the image. Now, the objective of this benchmark is basically to find an algorithm that can align the images that we acquire with subpixel accuracy. And secondly, is able to handle with large spectral variations. Why? Because our images are acquired at different wavelengths, and that means that you will get different spectral features in the image. And then thirdly, we need an algorithm that is able to handle or cope with large displacements, because images are rotated with respect to each other or have large translations. Now, in this benchmark, we have included 9 different methods, 9 different deep learning based methods that can basically be categorized into 3 categories. The first one are the traditional sparse key point and detection and matching algorithms, while the other ones can be categorized under the detector-free or semi-dense and dense alignment methods, which include, for example, GROMA and ELOFTER. Now, In order to make this benchmark, we have chosen to use Sentinel-2 data. So we have acquired 213 Sentinel-2 L2A images, sampled all across the globe, covering various scenes, so forests, agriculture, desert, snow. We used images at different resolutions, so 10 meters, 20 meter, and then we resampled a 10 meter to a 30 meter resolution image. So we repeated the benchmark at 3 different resolutions. And of course, since it's a multispectral mission, Sentinel-2, we can simulate spectral differences in the image. Now, one big part of this benchmark is how you create misaligned images, or how you create misaligned image pairs. So the first step is to sample homography matrices or transformation matrices. So for each Sentinel-2 image, we have sampled 100 homographies with the given translation, rotation, and perspective coefficients. An additional constraint when sampling these homographies is that we have always made sure that we have at least 25% overlap between the original image and the image that we want to realign to the original image. Well, just to be fair to the algorithms as well, they need some image features to work with, right? And to make it a bit more difficult, we have made sure that after sampling a homography matrix, that we also use different spectral bands. So we have our original image, and then we have our misaligned image, but sampled at a different wavelength or band. I will jump straight to the results because I only have a limited amount of time, but well, since we have repeated this benchmark at 3 different resolutions, and we have sampled 100 homographies per image, that means that for each resolution, we have repeated this benchmark basically like 20,000 times. So this will give you a fair idea of how good these methods perform. You can see that the dense and semi-dense methods perform pretty well. First of all, the metric that we used is a mean accuracy at a certain pixel threshold. This basically means the mean accuracy based on the average distance you get between the original image corners and the image corners that you get after realigning the image at a certain pixel threshold. Now, when you look at the results, we can see that the semi-dense and the dense methods seem to outperform your traditional sparse key point detection and matching algorithms by a fair margin as well. So since we were aiming really for the sub-pixel accuracy, these results are quite surprising. Because, for example, Roma is able to align images at all 3 resolutions with around like 80% accuracy. Yeah, when we now look at some visuals, you can, for example, see that when you look at the key point matches of alike plus the nearest neighbor matching strategy of the key points, that this method really fails at detecting and matching key points between 2 images that are acquired at a different wavelength. So in this case, I have chosen an image with the original band, so the image on the left side at the blue wavelengths, and then the misaligned image at the near infrared wavelengths. You can see that the matches really aren't too well or too good. But if you then look at the semi-dense and the dense methods, you can see that even though that there are spectral differences, huge spectral differences, that it does seem to find good matches between the key points. And this is very important to us because it gives us an idea of how robust these methods are. You don't want to fail, you don't want an algorithm that fails because you have some spectral differences. And this is just another example of how, for example, Roma and Elofter are able to detect and match key points pretty well. Yeah, let's keep the questions for afterwards. Thank you.
Our next presenter is Peter De Vries, who will presenting us the level 1 and level 2 uncertainty propagation and distribution for the next hyperspectral missions. Thanks.
Hi, everyone. My name is Peter De Vries, and so I'll be talking about some of the challenges and some proposed solutions for dealing with uncertainty propagation and distribution for hyperspectral missions. So let's start with some definitions. First of all, the error essentially is the difference between the measured value and the true value. This is a value we typically don't know, but that's why we have the uncertainties, which essentially is a statistical measure for the dispersion of our knowledge of the measurement. So essentially the probability distribution function of the errors. And so these uncertainties are really important because without them, essentially we cannot interpret or we cannot give a credible or reliable interpretation to our data. In many cases, there's multiple uncertainty components within a data set. And so the errors for these different components can be correlated. For example, in a systematic component, typically all the errors are affected by a single source, so they're all overestimated or all underestimated. And understanding this error correlation information is really important, specifically when we're combining multiple observations. For example, when we're averaging, random uncertainties typically go down with the square root of the number of measurements, whereas systematic uncertainties just stay the same. And so the plot here on the right essentially shows that as we're averaging more and more data, the contributions of the different components change. So the error correlation information itself, we can either store, for example, in an error correlation matrix. This is a matrix with values between 1 and -1, 1 being fully correlated, -1 anti-correlated. And so in the example here, we see that most of the measurements are correlated, but sort of the very highest brightest temperatures and lowest brightest temperatures are anti-correlated. We can also combine this error correlation matrix with the uncertainties themselves to then get to the error covariance matrix, essentially. But that one is a bit more hard to parameterize. Another way of storing this information is essentially by parameterizing it using error correlation forms. That's something that was defined within the Fiducio and QA4O projects. And it allows for a convenient way to essentially save that same information, but with very few parameters. For example, a random uncertainty component, we don't need any extra parameters. For some of the other ones, we might need to describe sort of the width of the distribution and so on. And so it's a very efficient way, memory-wise, to describe this error correlation information. I also put a link to the QA3O documents page, and there's some very useful guidance on this and some also some step-by-step guidelines to do an uncertainty budget and so on. So then some of the challenges for the hyperspectral data. Hyperspectral data sets are very large, and this has a few challenges when we try to propagate and store these uncertainties. For example, for every uncertainty component that we're storing, it will be by definition as large as the data variable itself. So for a typical example where we can quite rapidly talk about around 1 gigabyte of data. When we want to store the error correlation information, in principle, if we want to know the error correlation between every single spectral and spatial pixel with every other pixel, in this typical use case here, that would lead to 360 petabytes. So really unmanageable to deal with. Luckily, we can save this information, for example, separately per dimension, or we can parameterize it, and we can still keep this manageable, but to do it completely, it's pretty much impossible. Propagating uncertainties also becomes quite time-consuming because it scales with the data volume. And another challenge is that the characterization of the sensors from industry, specifically in terms of error correlation, is not always available, mostly because it's often not required. So there's a few things we can do to mitigate some of these challenges. First things here are some small compromises that could be made. And one thing is, for example, that the uncertainties and error correlation information can be stored with fewer bits. We can just use, for example, 8 bits for storing the error correlation matrix. Still gives us an accuracy of 0.01 in the 1 to -1 range, and that's sufficient for almost all use cases. We can also often, in most cases, we can save the error correlation matrices separately per dimension, and that massively reduces the amount of space required. So in a typical use case here to sort of 2 megabytes, which is much more manageable. In some cases as well, the error correlation information is constant. It just doesn't change from product to product. And in that case, it's also possible to store it separately in a separate file or describe it in ATBDs or in a QA for your effects table, for example. Beyond this, it's also necessary to essentially make a few choices about how we're going to store the uncertainty and error correlation and how we're going to propagate it. And so there's two main approaches that we can follow to keep the memory usage maintainable. One is we could split the uncertainties into simple components. And so for each of these simple components, we would then typically have a constant error correlation. So for each of these components, the error correlation doesn't change from product to product. And ideally, we want to then be able to parameterize it or describe it quite easily. Typically, in these cases, we can still have varying contributions of these different components. And that's why it's not possible to just store a single uncertainty component with a single error correlation matrix, because of the relative contributions, it would actually be changing. Another option is actually storing the uncertainty with the error correlation information in the file. In this case, we can often just store a single uncertainty component, but we can then parameterize this error correlation, typically per dimension, and provide it in the data files explicitly like that. About uncertainty propagation, there's essentially also two main methods. One is Monte Carlo. Here, depending on the number of iterations that we run, this can be a very time-consuming process, but it's very robust, and so it is often still a very useful approach. The other option is a law of propagation of uncertainties. Here, it can also still be time-consuming. Specifically, the calculation of the Jacobian in some use cases can be time-consuming. There, the benefit is that it often only has to be done once or a few times. But even just the multiplication of the very large matrices can also become quite time-consuming, and so sometimes it ends up taking even longer than the Monte Carlo approach. So here are some examples for some of the upcoming hyperspectral missions. I'm not going to go through this in detail, but as you can see, sort of different methods are being used for different products. Maybe one thing I should note here is I'm saying for level 2 here, I should really be saying for level 2A surface reflectance, because for level 2B there is other talks and posters that go into much more detail. And also Monte Carlo results can later still be used to sort of speed up the approach, but all of this is also still under development and subject to change. Then I wanted to quickly highlight the Comet Toolkit, which is a toolkit we've developed essentially exactly for this purpose. So it consists of 3 different tools. One is ObsArray, which is a tool for storing and handling uncertainty and covariance information. And it can essentially handle each of these different options that I've just discussed in a sort of and implement it in that way. Here on the bottom right, I show an example of how we store this parameterized error correlation information as attributes together with the data. And so this is a very useful way because we also sort of track the different uncertainty components to the different variables, and essentially this makes the approach completely machine readable. All the uncertainty and error correlation information is included right in the file. And that file can then, for example, be passed to PunPy, which is our uncertainty propagation tool, and it can parse all that information and use it either in a Monte Carlo or in the law of propagation of uncertainty methodologies. We also have a comment maths tool with some mathematical algorithms, and all these tools are available on pip and on GitHub, and we have some training material available and so on. So in conclusion, storing and propagating uncertainty information is very important, but it can be challenging. There's a few ways we can mitigate these challenges, for example, by parameterizing the error correlation information and storing it per dimension. Both the law of propagation of uncertainty and Monte Carlo methods are very useful, and the Comet Toolkit can be very useful in practically implementing these. And so if anyone is interested in using it or just wants to talk about uncertainties, please do come find me. Thanks.
I think at this point we'll invite all of our speakers to come back down. We're going to start a little bit of a discussion and kind of question and answer session here. I'm sure folks have lots of questions. As you're thinking a little bit here, though, we'll ask one just to start things off. So some of our speakers started to answer this a little bit, but maybe we can see if there are some additional thoughts. So one of our questions was, how much how instrument agnostic are the current state of the art algorithms kind of across the board, and kind of what level of customization, tuning, or auxiliary data is necessary. And I might add to that to challenge you, let's think about in this context that instrument agnostic includes any residuals that might come along with the data as they're delivered. So I know we heard that improving the reflectance can improve the algorithms here, but let's keep this practical for this conversation.
Yes, we also have been thinking about this quite a lot, and we've been working on this topic, and our opinion is that, in fact, the models should be left untouched. So the model is always made for certain, we should CHIME in our example. However, the image processing, there we can work on making it agnostic. For us, it's just a matter of making sure that we resample if needed. We can automatically remove spikes and so on. So we can polish and process the data to make it adapted towards the algorithm. In this way, we pretend to be agnostic.
Yeah, I fully agree with Joachim's comment here. I think the same accounts for snow and ice algorithms. We just need to make sure that we cover the needed wavelength ranges. So in terms of snow and ice beyond 1,000 nanometers, which not every instrument does. For example, DESIS, I think, does not cover this range. But otherwise, yeah, it's just a question of resampling and selecting the appropriate model, as we've shown in a few talks. That's the main point. But yeah, as soon as we have the resolution, that should be agnostic.
I think that the spectral feature approach, if we're looking for the right answer for 200 or 500 materials, then we require that reflectance to be very well delivered and in good shape. If we're going to talk about, say, relaxing that into these grouped classes of minerals, then I think we can be more sensor agnostic. So I think the results that I calculated around 50% or 60% agreement between the airborne data, which we are taking as the reference data, and the satellite data for some of these data sets. And we can improve that to 70, 80, maybe more, depending on how we group those classes. But I think what still we need to do on the mineral side is understand how to make those groupings so that we still get the right geologic interpretation out of the result. So certainly something where more work is needed to define that.
I think for the mineral mapping, let's say, problem specifically, if we could remove the, let's say, the training from the image itself. So if it is not image dependent, then we could move towards that, having a, let's say, higher resolution data, which then could be transformed into any sensor that we wish.
Just before we keep going, we'll keep answering the question, but in the meantime, if folks would like to begin answering the question put up on the board with the QR code, then we can discuss. Please.
Sure, I'll add my 2 cents about uncertainties. I think they're essentially the information we need to capture for any of the instruments is essentially the same. It's same core information that we need to capture, but typically we still need quite detailed knowledge on the individual sensors. And let's say, for example, how we can parameterize the error correlation information is very dependent on sensor to sensor. Different error correlation forms might be necessary and so on. So whereas the approaches can be very agnostic to the instrument, the actual implementation itself is probably quite instrument specific.
I think that approaching this question only by considering data is not enough. I ended my presentation by saying that data and algorithms, they should go hand in hand. So you can't just tackle this question by saying, I'm going to pre-process my data in a certain way, and it's going to lead to a instrument agnostic model. There are so many other things that one needs to consider. So there's model architecture, of course. There is the training procedure, there's pre-training procedure. So nowadays, and we see that also with LLMs, that certain LLMs are trained on these types of data sets and others on other types of data sets, and they respond differently based on how we query them. And I think it's the same stuff for imaging. You have to consider augmentations, how do you enforce invariance in your training routine. So I think there's just much more than just saying, I'm going to have a calibrated instrument. It's also, you also have to consider the other side of how do I actually train and choose my model properly.
Yeah, regarding band alignment, I don't really feel that these band alignment algorithms really care about how well your instrument is calibrated, how good the radiometric accuracy is. They just care about spatial features in the image. They do care about how well or how noisy or how much noise there is in an image. If there's too much noise, well, you can expect some degradations. But overall, I would say that alignment methods don't really depend on this well-calibrated instruments. Yeah.
Thank you for your initial inputs. Now we would like to open the discussion to the audience. If someone wants to give their 2 cents on the topic. Or if you have any other questions to the presenters. Well, maybe on the topic myself, actually, to start with, from what I see is that you, from most of the options that you are saying, that you kind of transform the input data to your existing models. And then my question would be, shouldn't the models not be performed better if you adapt your models to the actual data? It's, I don't know if you want to give some.
Yes, we don't really like that approach because we find it tricky if you start changing with models and you get different results and you no longer know, is it due to the data or is it due to the model, right? So we keep the model always as baseline, and we consider the image. The image needs to be process transformed anyway. We always apply smoothing, or in my case, we convert a reflectance into a product. So image is being processed anyway. So if you apply also to that and small resampling with hyperspectral data, at least for vegetation, very small resampling really doesn't matter too much in our opinion. But I can add one thing. Of course, the quality matters, right? But we can quantify the quality also because we see when on our resulting products how the uncertainty behaves. We have the estimates, but we always also have uncertainty. So of course, if the uncertainty starts to increase, we know something is wrong and that product is no longer to be trusted. So as long as we keep an uncertainty threshold, 20% or so, we are fine with our product.
Okay, maybe I try to add something regarding the validation as well of this algorithm, because sometimes we are focusing on how instrument agnostic they are. The algorithm, for example, for retrieving one parameter of snow and ice, but the best algorithm, it depends strongly on how one single variable of snow or ice is represented in the model that we are using for developing the algorithm. So part of the focus should be moved also on this representation of the variable, so, and the validation of it, because sometimes in the field it's difficult to find like a protocol to validate the liquid water content. It's like I measure here, there, and I get different values from the liquid water content, and Prisma has at least I must consider a 3x3 pixel, so 90 meter by 90 meter, and I have a strong variability within the pixel. So this should be accounted very much in which is the best retrieval algorithm for it. So this is fundamental in my opinion, because for the instrument agnostic, okay, I think I put in the presentation, if we are dealing with like 30 meter spatial resolution and more or less 10 to 12 spectral sampling, the algorithm I'm working on, they work quite good with this kind of data. And so the focus should be more on how we trust the retrieval algorithm.
Yeah, just add to this, Biagio, this is a very good point. And also, as I've shown in my slides, the question is how do the models represent our target? And if you talk about physics-based modeling in contrast to machine learning, usually these models like Motrend or DSort or others, they just take a spectral grid basically, so there's not too much like sensor-specific information except for the spectral information, like the wavelength centers and like the full width half max. So all other parameters are not coming in that sense from the sensor, so they are in that case agnostic. But the question is, do we have enough leverage with these spectral information to get the quantity out of it? And how does the model in these cases actually represent our target?
It's a good introduction to move to the second question, except if there are questions from the audience. I also wanted to add a last remark from my side, kind of listening to you all. So I would say as a summary, you kind of have agnostic algorithms, but you harmonize the data before. Basically, it would be kind of a trade-off. So we go to the question. Nope.
Yeah, I have two comments about this instrument agnostic data processing, right? So one of the thoughts is like if you want to have a method that is applicable to several satellites, you have to really take into account the uncertainty propagation within your algorithm. Because in the end, as Jochen was saying, you have to implement some data processing before applying your instrument agnostic algorithm. But in the end, this comes at cost of increasing some uncertainty of the input on the input data. So I think it's important to take that into account. At the same time, I think if you want to take the best of an algorithm, you have to really apply an instrument-specific algorithm. So it depends on the question, right? Like if you want to have one algorithm that can be applicable to several missions, okay, it comes at expenses of maybe higher uncertainties. But if you want to try to get the best of your instrument, you have to go to a specific algorithm when you know very well what is the characteristic of your instrument.
Maybe just to, okay, we have a few minutes left for this discussion, but this I think is also critical for tomorrow afternoon, okay? So just to focus a little bit the point here. We have to imagine that already today with all the wonderful imaging spectrometers flying today, Prisma, EMIT, DAISYS, and MAP, and more to come, as we've learned. We are capable of improving one of the most critical elements of each of these single missions, which is the revisit time, coverage time, right? I mean, we've seen earlier that you are aiming for a weekly effective revisit. This is not provided by any of the missions, not even CHIME, okay, which is the one with the highest, let's say, constant revisit over a systematic pattern. So you, in order to achieve your own requirements in the foreseen future, will have to rely on multiple missions to generate a single product, which is what you are interested in getting out of these imaging spectrometers. So in order to do that, there are certain things that have to be performed. So we are trying to, let's say, work so that this is the easiest possible process, or will be the easiest possible process with the future next generation missions. And for that, we have to understand what needs to be done. There will be always, even, and I quote Rob here, even within a single, one of the 3 spectrometers within CHIME, or one of the 2 spectrometers within SBG, the single satellite, there will be thousands of different spectrometers, one for each pixel. Each pixel has a different, slightly different wavelength vector, slightly different specifications, okay? So we have to understand how to deal with these discrepancies, which will always be there. It's impossible that we can work. There is no way that we can solve that beforehand, okay? So how do we deal with these discrepancies within single satellite, within a single detector, within, and particularly in between missions, okay? So that's the principle behind this discussion of instrument agnostic algorithms and product harmonization later on. So sorry for having taken a few minutes out of this time, but I hope that this clarifies a bit the context also for the future discussion today and tomorrow afternoon. If not, I'm happy to discuss. If I was not clear, I'm happy to discuss over the coffee break with any of you who needs to understand it more. And maybe I understand it better myself when talking with you, because it's really an open discussion. But we have to find a solution. So there are certain limitations in what we can do at instrument design level, at level 1 products, and also at level 2, let's say in the atmospheric correction. There are certain limitations in what we will be able to do. So at some point, you will be faced with discrepancies in between these data sources coming from the different missions, and you will have to handle that somehow. This was not the point, thanks, but this was not the point.
Wanted to show the second question. What is the level of customization required to be able to run on a different instrument? Yeah, quite some work, but reasonable. So basically everybody agree that everybody does fine-tuning or customization in all cases. Yeah. After the discussion of Marco, maybe also we could differentiate. So we want to discuss instrument agnostic algorithms, but I believe that there is no one answer. I believe also that the answer also depends of which algorithms for what. So for example, maybe let's say L1, L2 processor have different, L1, L2A processor has different answers than maybe L2B processors, for example. Because it cannot be that L2A processor is instrument agnostic.
Just very briefly to comment on the results. So for the first question, I think it was vast majority, yeah, only to some degree, are today can be considered agnostic with regards to the instrument specifications on the tiny differences between these missions that we've seen. And that most of you, at least most of those who answered, consider that the work to be done is reasonable. So, I mean, this is nice to see, because of course you will need resources for that, but it seems that you consider that these algorithms can be upgraded, adapted, or fine-tuned in order to become fit for purpose, despite not being it today. So this gives me some hope looking ahead.
Yeah, I think we are more or less online because we want to have algorithms which are agnostic, but at the end there are some details which can always has to be fitted. Actually, I think the question is very different. We are talking about more empirical or machine learning kind of approaches, or more physically based approaches where probably the different optimizations or generalizations for the instruments can be a little different. But the comment I wanted to make, I don't know if I have seen clearly the idea, but I know this is the case probably. at the end, we more or less all agree that together with the adaptation of the algorithm to the different instruments, we have to provide uncertainties, and then comparing the uncertainties, we will really be able to see how far we go. However, I see a point here because the uncertainty which is reported for machine learning algorithms is supposed to be the systematic uncertainty, while the uncertainty which is usually provided for the physically based or the classical, let's say, uncertainty is the random uncertainty. And actually with a different meaning, because when we talk about, and it was reported by the uncertainty discussions in the last presentation, random uncertainty is assumed to be reduced when usually increasing the number of measurements, while systematic is something you cannot handle. While in the machine learning community, what they call epistemic uncertainty is usually the systematic part, which is the one that you can handle, and the uncertainty that you don't know how to handle is the random uncertainty. I simply want to point out this point because we have to really go into this level of detail. Probably we will discuss again in the harmonization session and tomorrow about this topic, but I think it's a little more tricky than just saying, okay, with a little effort, we can accommodate the agnostic algorithm. This aspect of the different, very different interpretation of the uncertainties is also something we have to take into account.
Okay, we'll do a last comment here, and then I think everyone might need a coffee break and to continue this conversation there.
I just wanted to comment on your previous point about the systematic uncertainties. It's not that we cannot handle them. In principle, systematic uncertainties can be propagated through a processing chain or through a retrieval or anything like that. It's not like we cannot handle them. It's just that they typically don't improve the more data we take. It's not always easy to take into account properly the full random systematic and all the components that are included. But if you handle it correctly, it is all possible to handle. For machine learning, I agree, it becomes much more difficult to know what uncertainty they're really giving. Because I've never seen a machine learning algorithm that gives you an uncertainty with error correlation information. It'd be very nice to have, but I don't think that's something that exists at the moment. So that's maybe something where some further work would be really useful.
Well, let's thank our speakers one more time here. We certainly have a lot to think about and a lot to discuss again tomorrow. Thanks, everyone, and let's get some coffee.
The agenda if we want to enjoy our icebreaker later on. So please take a seat and we will restart as soon as possible. Grab the last cookie and please go back to the tribune. Okay, in the meantime, I would like to introduce the chairs of our next session on product harmonization. and Jose Moreno from the University of Valencia, and David Thompson from NASA JPL, and Sara Venafra from the Italian Space Agencies. Thank you very much for chairing this session, and I give you the floor to start with the first speaker. Thank you.
Good afternoon to everyone, and welcome to the product harmonization session. So we can start with the first talk about overview and status of the atmospheric correction intercomparison exercise.
Okay, good afternoon, everyone. Closer. My name is Noé Kren. I work for CERCO and ESA ESRIN, and I'm happy to present the current status and an overview of the atmospheric correction intercomparison exercise over land sites. And you can see here everyone who is in the coordination team of the exercise, and also all the participants who've kindly submitted their data and results. So what is the atmospheric correction intercomparison exercise? So we're comparing atmospheric correction processes and looking at their strengths and weaknesses, and also want to look at commonalities and differences. And how do we do this? So we agreed in a first workshop with the coordinators and the participants on an intercomparison protocol, and on data formats and which data we want to look at. And then in the second step, the participants use their atmospheric correction processes on scenes that were selected by the coordination team, and submitted this for analysis by the coordination team, who is then looking at a different validation site and comparing the results of the processes to those sites. And in the end, those results should be published in a paper. So initially, ASICS was a single exercise, but with time it kind of split up into different subgroups, because the algorithms and kind of user groups can be quite different. So now we have two atmospheric correction exercises, one over land sites and one over aquatic sites, and also an intercomparison exercise for clouds. And today I'm going to speak about the land sites, and we're looking currently at PRISMA and ENMAP data. And here you see the coordination team, so it's a joint effort between ESA and NASA, and we also have the support of different space agencies who've supplied data or processing. And here you see the current participants in the exercise who use their processors on the scenes we've selected. And you can see different organizations, universities, companies from the US, China, and Europe, and their processes listed here. So a bit more about the project structure. So as I've said, the first step was to agree on an intercomparison protocol. And then the coordinators actually downloaded and in some cases pre-processed the level 1 data for both ENMAP and PRISMA, and then made that available to the participants, who've then used their processors on those scenes and submitted the results back to the coordinators, who then do the validation and analyze the results and present those to the participants and discuss the results with them, to then do a kind of synthesis of the results and publish them. And yeah, right now we're kind of at the analysis and reporting phase of the intercomparison outputs. So which data are we looking at? So as I've said already, in this exercise, we're looking at PRISMA and ENMAP data. So 46 scenes have been selected for PRISMA. So what the participants received is PRISMA level 1 data. So the top of atmosphere radiance, radiometrically corrected, and then calibrated in physical units. And we're not supplying the original level 1 data, but we have some additional pre-processing that was done by JPL. And this is, on one side, the geocorrection to kind of correct for the geolocation offset of Prisma data. And then the addition of the sensor azimuth and zenith angles, because they're not part of the original level 1 data set for Prisma. And then you see the specs on the other side, so we haven't changed anything about those. And then in the end, it's in a HDR5 data format with Vini and Sphere data cubes, and then some additional fields about the geolocation, geometry, and the terrain. And similarly for NMAP, we have 44 scenes. We're supplying the level 1C data. So again, this top of atmosphere radiance, radiometrically corrected, orthorectified, and calibrated in physical units. And the data product also includes some masks about cloud and cirrus and so on. We haven't changed anything about the original data format, so it's in a zip file with different TIFF files and XML files, for example, for the metadata. And then we're also supplying, to ensure kind of common approach between the participants, an approach for calculating the sensor angle, because at that time it wasn't part of the NMAP product, and also a common solar irradiance model. And again, about the other instrument specifications, we haven't changed anything. So what are we actually comparing? So this is a bit in the kind of tradition of also the ASICS 1 and 2 exercises that we're looking at multispectral data. So we're still including aerosol optical depth and water vapor, although bigger focus is now on surface reflectance. And also what is different from previous exercises is that we're not looking at simulated data of aeronet sites, but looking at actual ground measurements for the surface reflectance. Similar to ASICS 1 and 2, the aeronet sites are used for the comparison of aerosol optical depth and water vapor. And you can see here the stations on the right. We kind of chose these stations, so there are 18 products for Prisma and 12 for NMAP, and we chose those for the stations that had both NMAP and Prisma data available, and try to kind of have a distribution over different continents and also land cover types. And we're going to look at these sites. So there's the measurement at the aeronet site is between 15 minutes from the overpass, and we're going to look at an image subset of 9 by 9 kilometers around the site, and try to look at some statistics and accuracy, precision, and uncertainty, although we have a much limited data set compared to previous exercises, so we'll have to look at what can be inferred from the information that we have. And then the bigger part is actually the surface reflectance. So the sites can kind of be, we have two groups. One is ground-based validation sites. So that is, on one hand, Radcarnet, where we have mostly desert, homogeneous desert sites. And we have scenes over all 4 Radcarnet sites. And then we also have some HYPERNet sites that we're going to look at that are also partly vegetation sites. And then we have also campaign data. One is only for Prisma, that is kind of agricultural areas in both Italy and Spain. And then we also have access to the NMAP validation campaign data. We again have kind of a lot of desert sites, but also urban areas. Some of them include also Radcarnet sites. And then we want to compare the algorithm retrieval over these sites. So to have a quick overview, we're using the level 1 Prisma and Nmap data, then the participants process those scenes, and we look at the results of aerosol optical depth, water vapor, and surface reflectance. So yeah, I just want to show some very preliminary results. So we are planning to also discuss the results with the participants. So I'm not going to name any processes, but rather show some example graphs of what the outputs can look like. And we haven't yet decided on which metrics we're going to use. So this is, yeah, very preliminary. So this is an example of a HYPERNet site in Witham Woods. It's a deciduous forest near Oxford in the UK. And on the left here, you can see the geographical context of the acquisition, and also the Prisma acquisition we have there. And the kind of white pixels are the ones that are used in this example for the intercomparison. So there's 4 pixels. And then on the right, we have the reference measurement with the corresponding zenith and azimuth angles. And you can see the reflectance and also the associated uncertainty for the measurement. And this is what some of the results can look like. So again, on the left, you have a scatter plot, and the colors indicate the corresponding wavelength over the site. So this is until, I think, 1,600 nanometers that we have to reference. And then on the right is the line plot, and on the lower side, on the lower bit, what you see is in green is kind of the uncertainty of the measurement, and then in the line is the absolute difference between the reflectance of the ground validation and the retrieval. And then we can also look at, so some sites we have more than one scene, so we can also look at all the scenes we have for that site and do kind of mean. And that's what you see for the line plot, and you see the standard deviation of both the satellite and the ground reference that are kind of overlapping quite well here with some outliers in certain bands. And then on the right side, you can see also for the same site, so for the same data, we can also look at accuracy, precision, and uncertainty. And again, we can see the outliers quite well there. And then you can also compare different processes. Again, there's some random examples of some processes that have participated in ASICs. And what you see is actually, the absolute difference to the reference. Just some examples to show kind of different behaviors of processes over different sites. So the one on the top left is Radkanet site, is the Baotou-San site in China. And there you can see a kind of common behavior, more or less, of all processes up to 900 nanometers with slight differences. And then if you look on the top right is a railroad valley playa of, and there again you can see kind of common kind of differences in some processes, and then some, or especially the one in blue, that seems to be behaving quite differently. And then on the lower left, you have Witham Woods, so there it's a bit harder to see some patterns that are the same for all processes. And then in Antarctica, we can see again that there's at least one processor that seems to be behaving much different to the rest. So yeah, this is some first results to illustrate what we're trying to do with the intercomparison exercise. And then also, as I said, we're trying to look at the aerosol optical depth and water vapor as was done in previous exercises. Again, you did simple scatter plots, you can see, and come to the last slide and the timeline, so I can go to where we are now. So we're kind of in between the results submission and the results workshops where all participants will come together. And the next steps until we discuss the results will be to compare different sites and groupings of sensors, of land covers, interpret results, give reports to the participants so that they can look at their own results, and then organize the workshop. Yeah, thank you for your attention.
Thank you, Noel. It's my pleasure to introduce our next speaker, Akpono Okujeni, who will be talking about harmonized Landsat, Nmap, and Sentinel-2 analysis-ready data cubes.
Okay, thank you very much. So I'll be talking about harmonized Nmap, Landsat, and Sentinel-2 analysis-ready data cube for streamlining multi-sensor environmental monitoring applications. So this is a collaborative effort with my co-authors, including Benjamin Yakimo, Andreas Jans, and Patrick Ostad, who are all here today. So we all know that the Landsat and the Sentinel-2 archives and related multi-sensor, combined multi-sensor time series, like shown in this example here for the Santa Barbara region in California, provide a valuable means for ecosystem monitoring globally. Now, with the launch of several hyperspectral satellite missions, this multispectral archives are subsequently complemented by hyperspectral time series, like this nearly monthly Nmap time series we were able to acquire over the past 1.5 years for the same study site. And these hyperspectral time series for sure open up new possibilities for ecosystem monitoring, whether we use them alone or in combination with this Landsat and Sentinel-2 time series. But if we want to really synergistically use these data sets, it's obvious that we need effective data harmonization and organization to do so. So if we dive into the multispectral world, we all know that harmonized multi-sensor analysis-ready data cubes streamline the time series processing on the one hand, but on the other also enhance time series applications. So we have temporarily denser time series through combining them from multiple sensors. And one tool my colleagues and I really like to use for this is, for example, the Force processing engine by David Franz, which really allows us to very easily create harmonized Landsat and Sentinel-2 analysis-ready data cubes based on a consistent radiometric preprocessing, an improved co-registration between Landsat and Sentinel-2 images, pixel grid alignment, and on top of that, this is very important, a data structure or data organization with a unified coordinate system and a consistent spatial tiling scheme, as you can see here on the left-hand side. Now, if we dive into the hyperspectral world, we, I think, all currently experiencing that the analysis-ready data we get are really a valuable source and open up new possibilities for environmental monitoring. But at least my experience is by working with this data, there is still some interaction by the user needed really to make this data ready to use, to be used. So for example, when working with the Nmap data only, we are dealing with large data volume. I think we've heard about this morning, that this seems to be an issue for users. So I'm really talking from the user perspective now. We don't have a consistent spatial tiling scheme, as you can see here on the left-hand side. And I observe remaining geometric uncertainties between images. And I think for time series application, we really need to make sure that the images align very well. And if we want to use the data together with other sensors, for example, Landsat and Sentinel, but maybe also Prisma, we may have different coordinate systems. We have, again, the image co-registration issue between sensors now, different pixel grid. So again, from a user perspective, I would say there is still some interaction required before the data is really ready to be used. So in this regard, I think streamlining the processing of, in this case, Nmap level 2 analysis-ready data as they are provided poses a research area where further enhancement may be beneficial for the user. And in this regard, the objective of this work is really to make use of various open source tools to develop solutions to streamline the processing of such level 2 analysis ready data. So we don't do magic, we simply use what is there and combine it to a workflow. In this regard, we are using the Nmapbox functionalities, we are using the Erosix package by Daniel Scheffler, who's also here today, and GDAL functionalities in order to improve the Nmap data organization by integrating the Nmap data into a consistent data cube, and also to harmonize the Nmap data with Landsat and Sentinel-2 data for multi-sensor applications. If you're interested in these tools, in particular, or you may contact Andreas Jans and Benjamin Yakimo for the Nmapbox and Daniel Scheffler for the Erosix package, or in general the Nmap preprocessing, and all of them have posters here. Okay, so our Nmap data covers 3 study sites in California. So in addition to the Santa Barbara region here, labeled Central Coast in the south of California, we also have a similar Nmap time series for the North Coast, north of the Bay Area, and in Northern California, Shasta Cascade. On the left, you see our successful Nmap acquisitions within the past 1.5 years by time and average cloud cover, and you see that we were pretty successful in receiving data, and we have about 40 observations per study site available. So to produce our harmonized data cube, we first use the force processing engine to produce a harmonized Landsat and Sentinel-2 analysis-ready data cube that comprises all Landsat and Sentinel-2 images that were acquired since 2020. But this year is arbitrary, so we can really go back until the 80s, Landsat 5, easily. And on the left, you see the Landsat and Sentinel footprints we used to do so for our 3 study sites. And on top of that, our new data cube tiling system. So we decided for 30 by 30 kilometer tiles and the unified coordinate system. As we are working in California, we decided for the California Albers projection. Here you see an example of such a 30 by 30 meter Landsat reflectance product that comes out of force and the associated quality layer. Here it's also a combined layer, and how the data is stored on disk. Now, to include our Nmap data into the same structure, we implemented a workflow that automatically unpacks and imports the Nmap level 2 product. And the import is so far important because it handles also the metadata effectively. So that's an Nmapbox functionality, for example. And then we did a spatial alignment and the tiling. And for the spatial alignment, we did a reprojection and used the Erosix package to do a co-registration and a pixel grid matching with the Landsat base image that we got from our Landsat Sentinel-2 cube. And for sure, for tiling, we used the same tiling grid that we used for the Landsat and Sentinel-2 cube. And as a result, our previously generated Landsat and Sentinel-2 data cube now seamlessly integrates the level 2A Nmap products, as you can see here, as well as the related quality layer. And this quality layer is also a combination of the different quality layers that are provided with the level 2A products. And I think this new data organization of the Nmap data in general helps the user in 2 ways. First of all, processing the data, especially the masses of data you will have when you have time series, is really easier in my opinion. But second, also, it really enables multi-sensor time series applications. So we have now really spatially aligned Nmap, Landsat, and Sentinel-2 data. And this is what you see here in this animation. A Landsat 8, Nmap, and a Sentinel-2 image that we're taking almost at the same day. I think there is a difference of 1 to 2 days between those images. And I think you really nicely see how well they align now. Here a zoom in just to illustrate how well also the pixel grid matches between the different sensors. And yeah, you have to say the Sentinel-2 data is at 10 meter, whereas the Landsat and Nmap data is at 30 meter. Below you see a corresponding spectrum of the surface from all three sensors. But I really have to say here, the focus so far was mostly on the spatial alignment, I would say, of the different data sets, while a comparison of the reflectance data was not done so far. And maybe this is something one may look into in future. Okay, I would like to end this talk with one application example on how we use the data cube. And I must say, so far we only focused on using the Nmap data and not like the synergistic potential of Nmap with Landsat and Sentinel. And we mainly focus on the retrieval of non-photosynthetic vegetation, green vegetation, and substrate cover fractions across ecosystems. We are really able to derive time series, as you can see here in this plot. And we actually do this for the 3 study sites in California, but also for a 4th study site in Namibia, where we have a similar near monthly Nmap time series available. There will be more coming on the talks on Friday on the time series, MPV time series retrieval. Okay, with this I would like to conclude, and I received those 4 questions by Marco, and I tried to answer the first 2. So with regard to the question, how does your work contribute to improving harmonization, and also with regard to the question, what aspect of harmonization can most benefit users? I think, first of all, this work provides a workflow that integrates level 2 data from different sensors, in this case Nmap, Landsat, and Sentinel-2, into a consistent data cube, enabling multi-sensor time series applications. And I think this approach is very generic, so if I have Prisma data or Emmet data, I could easily also integrate these data sets into this data cube structure. And the second, with regard to what aspect of harmonization can most benefit users, I think from a user perspective, users may most benefit from harmonized level 2 data. So if they are really radiometrically and geometrically consistent, I would say, and also an more effective data organization, because the way the data is provided now is simply different depending on which sensor, be it Prisma, Sentinel, Landsat, Nmap, they come just differently, and having a way of organizing them better makes it easier for the user. Yeah, but I guess due to sensor differences, it's likely that really a proper harmonization of level 2 data is not feasible. So in this case, I think secondary adjustments like the secondary geometric correction we did are a solution for this. With this, I would like to thank you for listening.
Great, thank you. And it's appropriate, I think, that this talk follows. In counterpoint to the geometric aspect of harmonization, there's a spectroscopic aspect, and that's part of the perspective that we take here. This is a report out from a working group that was founded over a year ago now by the CHIME and SBG teams to try and work together to understand how we can make our level 2A reflectance products more intercompatible with each other. It was led by myself and Valentina, and I think I can say that it really has had a material impact in how the missions are approaching atmospheric correction. There are certain changes, design decisions that we've made, at least I can say on the SBG side, that are different than we might otherwise have done, that will have the end result of making these products more interoperable, more intercompatible, and for the benefit of the users. And so I'll take a few minutes now to talk about our own perspective that we took on harmonization, to lay out a few foundational concepts for atmospheric correction specifically, and how we approached harmonization in that concept, or in that context. And then at the very end, I'll provide some of the SBG and CHYME choices that we made in our atmospheric correction algorithms, so you can see how provisionally they're stacking up, to give you an idea of what you might expect from CHYME and SBG products. Okay, the challenge you're probably all familiar with, but pays repeating, is to take the radiant spectrum observed at the sensor and then infer this challenging optical system here, including scattering and absorption from different atmospheric gases and aerosols, and more significantly, the reflected component from the surface, and come up with a model that explains this so that we can extract the critical surface reflectance spectrum out. And forgive me for a moment for using the term reflectance loosely. We'll get there in a moment. But for now, think of it roughly as the fraction of incident light that's reflected back in the direction of the sensor. And this is, of course, where all of our Earth surface properties live, in this reflectance. And it's presumably somewhat invariant to observer and solar position and the state of the atmosphere at that particular time, which makes it more useful for building maps of surface phenomena. Now, everybody, for the most part, agrees on what a reflectance quantity should look like. And moreover, there's pretty good agreement, I think, across sensors already on how to calculate radiance values, how to calibrate the digital numbers of the sensor to get a comparable quality. The same is not so of reflectance. In fact, there are a wide variety of different approaches. And so in contrast with the level 1 radiance products, we see a plurality of different methods to solve this problem. So why are there so many different alternatives for atmospheric correction, like we saw initially in the ASICS presentation? Well, first let me talk about why harmonization is important. Harmonization of level 2A is really foundational, in that it's necessary for all of the downstream processing that comes afterwards, all of the mineralogy, all of the vegetation properties that we'd attempt to retrieve, the water column properties, all depend on getting accurate surface reflectances. And differences in surface reflectance can impact everything, as we've seen. Harmonization is especially useful for CHYME and vSphere. We care because as Marco said before, one can significantly improve the sampling frequency of both of these missions by using products from both sensors together. If we are able to use either reflectance from either mission in similar downstream processing, we can increase the sampling frequency to capture that weekly revisit time that we'd really like to achieve. And this is critically important for SBG science objectives and the applications objectives of CHYME. As I mentioned, it's important to harmonize because there's no single gold standard solution, and missions will likely devise their own atmospheric correction modeling assumptions. And I'll, again, in a moment, I'll talk about why that might be the case. And so this requires that we balance consistency with a need to experiment and have a plurality of different measurement approaches so that we can learn more about the problem and how to continue improving our algorithms in the future. And finally, this is an important problem because the results of all those downstream algorithms can be highly sensitive to changes in those atmospheric modeling assumptions. Atmospheric errors tend to create spectrally correlated artifacts and residuals in reflectance spectra that can be particularly detrimental to shape-fitting algorithms or empirical algorithms that are fit on some other sensor. So these are exactly the kinds of artifacts that we'd like to avoid to get back to that beautiful white Gaussian distributed noise that we'd really love to have in order to make our algorithms function well. Okay, so atmospheric correction, there's a plurality of approaches, largely because it's an underdetermined problem. There's no one solution. If you think about the forward modeling problem, which I've written out here with some simple notation, we have a state vector describing of parameters describing the surface reflectance, the atmosphere, and maybe even parameters of the instrument too under certain conditions. And we have a forward model, typically a radiative transfer model of some kind that can use that. It's a recipe for calculating the measurement that we would make at the sensor. And these radiative transfer models are typically a layer cake of different atmospheric layers populated with appropriate constituents of gases and aerosols that can solve the system of differential equations to figure out what the measurement at sensor would likely be. And so note that there are more parameters in X. X is a vector of size n, where n is larger than m, the number of measurements. So it's an ill-posed problem. This is the problem that we'd actually like to solve, the inverse problem, where we have the radiance and infer the most likely state that gave rise to that. And in order to do this, we have to bring some additional constraints to bear on the problem. And it's differences both in the modeling assumptions that produce the radiance and in the constraints that one imposes in the inverse problem that lead to all of these different atmospheric correction options. Okay, so some guiding principles that we used in approaching this harmonization question as a working group. How do we think about how best to harmonize these products? Well, we felt that differences in the definition of product, the definition of reflectance, are to be avoided because that's really what prevents intercomparisons or interoperability. If you have two different definitions of reflectance, then you have to introduce a model in order to translate between them, and that's something that we definitely don't want. However, we felt that in contrast, differences in the forward modeling, the radiative transfer assumptions, the atmospheric parameterization, et cetera, and or the inversion approaches are inevitable. They can't really be avoided. Sometimes a plurality is actually a good thing if we're driving towards the same fundamental measurement, and they don't prevent interoperability, provided we have some appropriate uncertainty accounting that lets us fuse the resulting data in a principled way downstream. So this is how we approach the problem. Let me back up for a minute. I mentioned that surface reflectance is a complex quantity, and in fact it is. So one of the first things we talked about is what do we mean by surface reflectance at all? And there are many different definitions. In order to talk about surface reflectance, we have to talk about what surface is doing the reflecting. Is the surface that of a virtual polygon? It's pixel-shaped and sort of set at ground height and aligned parallel to the geoid. That's the assumption that the emit mission uses, for instance. And that's a well-defined surface that one can calculate the reflectance of. Or an alternative would be to consider it a terrain facet, take that same polygonal virtual pixel and now tilt it so that it's aligned to a local digital elevation model. That's another perfectly valid definition of the surface for which you can calculate a reflectance. It might have certain advantages, particularly if you are comparing it to a measurement that was made relative to that local surface normal. But it comes with its own challenges too. For example, what if the digital elevation model doesn't align perfectly with the terrain? There's that discussion in the snow discussion as well, that even minor subpixel differences in co-registration with the DEM can potentially have large downstream impacts on the resulting errors. So there are pros and cons to each of those definitions, and they're both perfectly valid reflectances. Similarly, the quantity itself, are we talking about the hemispherical directional reflectance factor? That is the fraction of the total downwelling radiation onto the surface from the vault of the sky and the direct beam from the sun reflected back towards the observer in the observation direction. Often, these reflectances are BRDF corrected, meaning we take that directional measurement and we simulate some other observation geometry so that we can make a comparison with other sensors acquiring at different times, different solar angles and look angles and all of that. If we then take those directional measurements and through some model simulate what the nadir observation would be, presumably that's more generalizable, but of course it comes with its own very discipline-specific modeling assumptions that have to hold for that to be accurate. So again, there are pros and cons to both approaches. The aquatic community has its own definition of surface reflectance. Remote sensing reflectance is a directional quantity. It's a per steradian quantity, and it generally excludes the specular sun and sky glint off the surface of the water, because what that community really cares about is the reflectance coming up, the upwelling signal coming up from the water column. And so that's the reflectance in the remote sensing reflectance, the RRS. And so that's really the quantity that they would like to see. And then finally, what strategy is used for geolocation? If we're defining different surfaces for which the reflectance is calculated, it's important that those surfaces are aligned with each other in order for us to do some sort of a comparison. So that's the presentation immediately prior. A little bit more on these topographic effects, just to flesh out that concept a little bit. This is from Nimrod Karman's paper, Shape from Spectra, in which he describes the spectral shape of downwelling illumination. So as a terrain facet tilts away from the sun, then you see a slightly different solar incidence angle onto that surface facet, and that foreshortening means that there are fewer photons falling per unit surface area, and you get a reduction in the direct illumination. But there's also a shape effect because of the balance between that direct illumination and then the diffuse illumination coming from the sky. So you actually end up with a different color of illumination onto the surface. And so in order to make the most accurate measurements, particularly over surfaces like snow, it's really helpful to use a terrain relative orientation. Here's another example of glint removal. So I talked about glint, the sun and sky glint being these nuisance signals that we'd like to remove from the surface reflectance of water. This is work by Marcel Koenig about actually looking at airborne data with using a variety of different atmospheric corrections. And you can see that these unglint corrected spectra that lift off the zero line due to the additive signal coming from the specular sun glint drop comfortably down to zero when the glint is accurately modeled. And so this turns out to be a really important thing to do to get the water leaving reflectance. Okay, so this is the punchline. After all of our discussions, we came to this conclusion about the different parameters that we would use. This is all provisional, mind you, for SPG and CHYME. Welcome all discussion and feedback on these, of course. For the definition of surface, I think CHYME intends to use a topography relative definition of surface that is relative to a digital elevation model. SPG VSWR will likely adopt the same approach, particularly due to our requirement to measure snow surfaces, which are very sensitive to the balance of direct and diffuse downwelling illumination. The digital elevation model for both missions is likely to be the Copernicus DEM. The EMIT mission has historically used the NASA DEM. Has historically used the NASA DEM, but we feel the Copernicus DEM is probably the more accurate one for SPG's use. Similarly, both missions will be using the Sentinel-2 global reflectance image for co-registration of images, which means that because we're all co-registering to the same image base map, the two should hopefully mosaic fairly straightforwardly. Now we'll see. We've noted that even the same sensor using the same geolocation strategy doesn't always co-register with itself, and so this will be a continual challenge, but we think that using the same underlying base map to recognize those image landmarks and lock down our images to their locations will help that process along. At least we're all working from the same fundamental definition of where they should be. As to the BRDF correction, the capability will certainly exist in CHYME, and SPG VSWR is likely to not perform any BRDF corrections or BRDF adjustments on the distributed level 2A product, although that capability will be implemented in the level 2B products on a product-specific basis. So for example, the vegetation algorithms are likely to use a BRDF correction specific to vegetation as a pre-processing step in order to facilitate, to make their results more generalizable. From there, the two teams diverge a little bit, although the radiative transfer model on the SPG side is still very much under discussion. There are several options that both teams are investigating. Irradiate, we've seen already in the earlier training session, LibRad-Tran is another excellent radiative transfer model. On the SPG VSWR side, we've historically used ModTran, but are moving in alternate directions, both for an open source alternative, but also for speed. Things like PCRTM, vSmartMOM, or SRTMNet, which is an emulation strategy. We independently came up with a Peter Gega-based model for our glint modeling, which is kind of a fun outcome. This model, which has been spearheaded by Regina Eckert and Nicholas Bohn at JPL, it includes both independent sun and sky glint coefficients for every pixel. We're likely to use TSIS, which is fast become a community standard, as the solar radiance model, although in both cases this is still under discussion. That's what the asterisk means, I believe, is that it's still quite provisional. Both teams recognize that aerosol parameterizations are a major challenge that we should address and improve, I think, for better atmospheric correction performance in the future. It's a no-brainer to retrieve aerosol optical depth, but if we could get an angstrom exponent as well to understand the spectral character of that aerosol extinction, then that would be a very useful thing to do, and we're both considering that as well. And then finally, along with the L2A, will come a bunch of masks for different land cover types and for exclusion of clouds, cloud shadow, et cetera. And we'll continue working among the two teams to try and align those mask definitions as well. All right, so finally on to the seed questions. How does this work contribute to improving harmonization? Well, I think we've really focused on aligning those product definitions to the extent possible so that the quantities we're measuring are the same quantities. How we get to those quantities might be different paths up the mountain, but we arrive at the same place. And then to the extent possible, to the extent it makes sense and that the teams can, we would like to align the forward modeling assumptions as well. What aspect of harmonization can most benefit users? We feel, again, that definitions are critical. We also think that rigorous uncertainty quantification has a role to play in all of this because at the end of the day, with two separate quantities, two separate measurements to compare them or combine them, you need an error bar on both. At what level of processing is harmonization most necessary? Well, this is my own parochial opinion here, but I think, of course, the lower level products are quite important, the radiance and the reflectance. The reflectance may be quite challenging from a practical perspective because of the plurality of all approaches, but I think if we start from common definitions and understanding, that will certainly help. And then finally, what's more important, the data formats or harmonization on information content. Again, this is from the producer perspective more than the user perspective, but I think that information content is foundational and we really have to work together to make sure that we're measuring the same thing. And then once those measurements are produced, we can work on formatting, although that's important work that needs to be done and will continue for the next 2 years as well. So thank you very much.
Thank you, Del. So we can move to the next speakers, Andreas Bockert-Gartner from DLR with a novel sensor radiance harmonization method.
So, yeah, hello, thank you for having me. This is actually the short version of a talk my colleague Klaus Köhler will give next week on the pre-flight calibration workshop, also at ESTEC. So if somebody is here, yeah, unfortunately you have to hear some parts 2 times. So this is more about the airborne instrument. This is our airborne imaging spectrometer HYPERSPECTRAL. So we operate now a HYPERSPECTRAL B system, so we call it ourselves. These are the HYPERSPECTRAL Svenia 3400N and a sphere spectrometer. And the important thing is the N here, because the instrument is NICU sampled, because we have more 700 channels and more than 3,000 spatial pixels. The sensor operational since 2023, and yeah, are typically hyperspectral sensors except for the N, for the NICU sampling. But to the heritage, we operate in the HYPERSPECTRAL system since 2012, acquired it in 2011 as MAP demonstrator. And these systems were extensively calibrated in our lab. So our advantages with airborne sensors, we get them back, so not like satellites, which are gone usually. And therefore we can recalibrate after each campaign. This is our calibration lab, the calibration home base. This is actually an ESA term, because ESA co-founded the lab. It's operational since 2007. And we can basically calibrate most of the relevant instrument properties, and it's under continuous development. So on the right edge, you can see one of the instruments we recently calibrated. This is an HYPERSPECTRAL 4 instrument built by NASA JPL and operated by University of Zurich. Of course, we calibrate our own instruments, and we calibrated with equipment and knowledge we gained here to the MAP mission. So these are some results of the calibration of the instrument. You can see we have for each pixel an individual spec response function. So none is the same. And it's actually quite, so the worst part is in the center of the detector. So you can see it on the left. These are the spectral response functions on different parts across the complete spatial columns. And you can see we have kind of a double peak. And so, yeah, what's the center wavelength? What's the resolution of this pixel? This is not really well defined. So, and also for other parts which are not in the center of the detector, we have kind of a shape which is not very Gaussian, which is usually the case. Most you give, for most missions, for MF instance, there's only the center wavelength given and the resolution, so the FWHM. But often this is not the whole story. And we have kind of similar results for the across-track response functions. So the same spatial column doesn't look at the same spatial position. So we have in this situation, we have actually a very well calibrated instrument, but the available level 1 algorithms usually only correct for smile and keystone, or and higher level products don't make use of the information we have here. But how can we make use of this information? How can we make data from different data locations, detector locations comparable? How can we make data from different instruments comparable? And how can we actually reduce data complexity? So especially in this case where we have a highly oversampled instrument. And then is the question, the final question, do we really need to track the response of each individual pixel in higher level products? So I'm sorry, it's the second last talk this day, and I have some off, but I will make it quick. So we have, on the right side, is a high resolution spectra you usually have in nature, and then it's convolved with the instrument responses. So this is the F function here. And what you get at the left side, this is actually the discrete instrument response for each pixel. So for simplicity, this is only the spectral case. We also have the case in the across-track domain and in the long-track domain. So again, on top, the equation from the slide before, we have a system A, and then we have another system which has different response functions. In this case, what we want to have actually Gaussian response, the system B. And when you compare the two systems, you see, okay, they don't align, of course. They're not the same. So, and the actual goal is we have a system A with the radiance from system A and want to convert it into system B. And how can we do this? We have a signal vector and want to convert it to another signal vector. The usual answers, we have a transformation matrix, K here. And K actually maps each pixel of system A to each pixel of system B. So there's a dimension of all the number of pixels of system A times the number of pixels of system B. And remember, each pixel has individual properties. And the thing is, K only needs to be calculated once. So we actually need to find K, which transforms one system to another, only once, and we could apply it always on system A spectra. But how do we find K? So I won't go in detail how we find K, but the basic idea is we use the cross correlations. So we have the cross correlation of each pixel from the system with itself is on the right side. So the disturb response functions with the neighboring response functions. And then we have on the left side the correlation of a system B with system A. So here we have, as example, a perfect Gaussian response with the correlation, which is the blue area with the system A. So what we need to do is at the end optimize this equation, because the metric is CAA and CBA are both instrument properties. To solve for K, usually we use Tikhonov regularization, so this would be way much time to explain it here. So the mathematical background can be found in this publication if you're interested, but we won't. There's a lot of math. So this is our current high specs linear 3400N processing settings. So we have, for the original instrument, as I said, more than 3400 spatial pixels, 700 channels. We have SMILE, we have Keystone, we have non-constant angular and spatial resolution, and we have very complicated SF shapes. And what we actually want, what we define an ideal sensor with less pixels, less channels, no SMILE, no Keystone, constant angular resolution, and also the constant spec resolution, where we do kind of with super resolution of certain channels and with a perfect Gaussian model. So the spec response on the left is converted to a perfect response on the right. So the algorithm works. First, to show this, we use simulations. We have here a test scene. we convolve it with the instrument model of a sensor B, so that we have an ideal image to compare with. And on the right side, on the processing chain, we have the real sensor model with the complicated response function shapes. Then we get the distorted image. We apply a transformation, so the transformation matrix, get then the so-called the sensor B transformed image, and then we compare it with the ideal image. And so on the top is the spectra in blue, how it looks after transformation. And the orange curve are the uncertainties, or better to say the error from the transformation. So we have errors which are below 0.2%, and they are mostly in the region where we do super resolution, so where we actually increase the resolution of the instrument, sorry, which is caused by the distortions in the center of this spectral filter, and at the beginning of the detector where the resolution is a bit less. So question is how we can propagate uncertainties. So there's a linear operation, so spectral uncertainties transfer linearly, and radiometric uncertainties we can actually propagate just with the transformation matrix as shown here. The graphic here shows the relative noise change after we apply the transformation matrix. So in this case, due to the smart binning, we actually reduce the noise of the instrument by a factor of 3 to 4, up to 5. Except for the center bit, where we do, again, the super resolution and the top of the spectral range. So simulations are one thing, but most interesting are experimental results. So this is some of the results from a spectral mercury calibration lamp, which was coupled into integrating sphere and then measured with an instrument. So on the left is the result from 2 spatial pixels from the original system, where you can see, there's a difference of the response between the center of the detector and the edge. And then after transformation, okay, we do the smart binning, we have less pixels, but actually we have a constant response function. And you can see that the curves actually fit quite well in the center. So for comparison, you can see in blue, we have a difference of up to 20% of the spectral measurement from the original instrument. And after the transformation, we get down to 2%, and it's almost perfect for the second peak. So what's the application of this method? For instance, we can create an ideal high-specs from high-specs real instrument. So we get the harmonized Lagrange product due to smart binning, reduce the size of the spectral arrays. Then we have high specs we can use as a chime validation unit by transforming the spectra to chime spectra. We can transform, for instance, chime spectra to Sentinel-2 for cross-validation. But what we can't do, for instance, is to transform to Sentinel-5P spectra, of course, because this would be very wishful that this would be possible. So, conclusions. We have the matrix response function harmonization as a tool to correct several optical artifacts, reduce data size by smart binning, reduce complexity of downstream processing, deliver level 1 products that are easier to adopt by the community. And I showed now for the case for an oversampled instrument, but this works also for undersampled instruments to a certain degree. And our findings, actually this may be a bit controversial, have implications on the design of future sensors. So oversampling improves data quality. Smiling keystone shouldn't drive the optical design, and knowledge of the response function, including on-orbit changes, is of paramount importance. Okay, thank you.
Thank you. Our final presenter of the session is Parth Naik, who will be talking about a hyperparameter optimization algorithm for unmixing multi-scale hyperspectral remote sensing data.
So, hello, my name is Parth Naik. I'm a scientific employee at Helmholtz Zentrum in Dresden, and today I'm going to present a hyperparameter optimization algorithm for efficient unmixing of multi-scale hyperspectral remote sensing data. So, as you can see from the title, it doesn't say much about harmonization, but we'll shortly see how we do the harmonization. So, our problem here that we basically address is when we see our hyperspectral data set at multiple scales, the N members detected at one scale is not a representative for the other scales. So when you go from lower resolution, higher resolution to a lower resolution data, small features identifiable at higher resolution blend into their neighborhoods, creating mixed pixels. So to do some unmixing or to determine mineral abundances, we propose a method which harmonizes data at feature level. So we'll shortly see how we do that. But for doing that, we use data sets that are shown here. So the study site is Marincas in Namibia, and the data sets are HYMAP, which is an airborne sensor, 5-meter resolution. And then in the satellite side, we use NMAP and Prisma data. So as you can see, they have slight difference in the radiometry. And of course, HYMAP has a very high resolution of 5 meters and NMAP and Prisma at 30 meters. So this is our proposed framework. What we do is we take the high resolution data. We do the unmixing for 2 classes, calcite and dolomite. We purposely choose these classes because, as you can see, they have a very close absorption signature. So we can really test if our framework is efficient at harmonizing these features from different satellites, such as Prisma and NMAP, and if they, in the end, give a plausible or a good unmixing result. And what we do is we calculate these high-resolution accurate abundance products from HYMAP, and then these are used as references in our optimization framework. So our optimization framework is linked with the satellite data, which is at a coarser spatial resolution. And what we essentially want from our optimization framework is explainable features, so that we know what features are going to be harmonized in the end, so that we have a good end product, that is our abundance maps. And then we do some qualitative and quantitative of the result. So this is our optimization framework broadly. So this optimization framework basically the non-dominated sorting genetic algorithm, it's basically used to create trials on spectral bands. So what we provide this optimizer is a structure or structure of the index. So we say, let's say B1 minus B2, we provide it an empirical index. What this algorithm has to do is create trials on the spectral bands of the hyperspectral data, and precisely point out which bands are most suitable to be fitted in this empirical index, so that I can have the best prediction of my target abundance. To do this, it's a multi-objective optimizer, so it's not just a traditional prediction where you just determine the R-squared score of a model, but it is multi-objective. So our optimization functions are the R-squared score, which tells you about the model, what variance is the model learning. the mean absolute error, which is like the average errors in the prediction, and SSIM, which is the structural index, structural similarity index measure. So our optimizer basically needs to balance all these three optimization objectives so that it can produce the best result. So this is these are some details about the optimizer. It's very much theoretical, but just to show how it works. So it basically works by creating Pareto fronts. So what it is initialized randomly, and it creates these combinations of bands which are formulated using genetic operations such as mutation and crossovers, and basically it needs to optimize all these objective functions to create a Pareto front, a front which collectively optimizes all these three objective functions at the same time. So these are the results. On the very left, you have the dolomite predicted using Nmap. In the middle, you have dolomite predicted using Prisma, and this is our reference HYMAP. You can see there is quite similarity, quite accurate predictions. You can also see the ring structure of the dolomite predicted very accurately in the low resolution maps. And this is for calcite. So you can see calcite is also predicted very accurately when you compare it with the reference. So now this is where the harmonization thing comes to. On those scatter plots, you can see that our initial data, that is Nmap and HYMAP, the spectra is quite perfectly, the reflectance is quite perfectly correlated. But when you compare Prisma and HYMAP, you can see that clearly there is some deviation in the sweet region. So although, and when you see the Nmap and the Prisma correlation, again, there is quite a deviation in the sweet region. So when there is this inherent difference in the reflectance of the images, even harmonization, if the data is harmonized at image level, let's say if you harmonize these reflectance images, the end product might not be able to do what you expect it to do. So what we did here is we created a framework that precisely point out which wavelengths are in Nmap are equivalent in Prisma, so that you actually have a feature level harmonization which delivers you the best accurate prediction of any abundance map. So primarily, if you can see that the whole framework, it identified the primary signature of these two carbonate minerals, that is in the SWIR region. There was an effective separation between the two very similar carbonate minerals. Also, we did it using only a very small fraction of the spectrum. So we dealt with this excess information that we have, and we pointed out correctly which fraction of bands should be used for accurate prediction of our target minerals. So the achievements of these methods is we came up with an automated feature engineering mechanism. So what you do is you just give it a structure of the index. It figures out which bands should be fitted, what features should it calculate, and how it should predict your target mineral or any target variable per se. Unlike unmixing algorithms, this approach facilitates explainability and tunability. So you can actually know which bands are contributing to your predictions, and also using the Shapley values that I just kept, it's a part of our framework. You can tune how much information should go in for your prediction. Also, it proved very robust in handling the redundant and trivial information that is always a pain in hyperspectral data. And yeah, it also has diverse ranging applications. For example, we used it for sensor selection, especially those were the ground-based sensors where we have these drill cores, and we have this sensors which 3 different sensors sensing in the Vernier sphere and the long wave infrared region. So there are 20 different mineral classes, and you need to optimize which sensors need to work in tandem to precisely identify the target mineral. And also we used it for resolution enhancement work, where the Nmap and the Sentinel data were harmonized, also at the feature level. So what we did is we computed, so we predicted some latent features from Sentinel data. So these latent space was created using decomposition methods. So there were various decomposition methods that were tested on Nmap, and you create a latent space which is predicted using Sentinel, and then you just compute the differences between the low resolution hyperspectral and the high resolution hyperspectral to identify which high frequency details need to be pushed into Nmap so that you have an enhanced hyperspectral data. So here is our enhanced Nmap data at 10 meter, and you can see these hull-corrected spectra of a few pixels, which are very nicely enhanced. So, oh, sorry. So the final discussion on the questions. So contribution in improving harmonization. So what we demonstrated here is a feature level harmonization. So inducing features in low resolution hyperspectral data using high resolution product through a feature level harmonization actually helped us to navigate through the various complexities that are with different data sets that are sensed using different sensors, different satellite sensors. And it enabled us to accurately predict many of our target minerals. On the aspect of the harmonization, how does it benefit the user? So we have explainable features, so we actually know which particular wavelengths are contributing to the prediction of our target. So we pinpoint, accurately pinpoint the informative spectral bands in low resolution, but based on an information that we have gathered from a high resolution product. And on the harmonization of formats or information content, I say both are equally important. Harmonization of formats actually help you to navigate through logistical challenges such as processing, integration, and pipelining of your data, so best for all practical reasons. And if you go with harmonization of information, information is equal to insights. So of course, this helps you in improving your product accuracy, and of course, it's a good means for a better time series analysis. Thank you. So here are a few projects, but okay, we can. Thank you.
Thank you. We're about to open it up for questions and general discussion, but before then, we have another QR code for you all to photo. The first couple of questions of this survey are going to be free response, so just type 1 or 2 words that describe your answer. And while you're working on that, we'll open it up for any questions for any of the speakers.
So David, you mentioned the challenge of trying to handle these underdetermined problems. And in the last presentation we saw here, it seems like one of the things that's also underdetermined is how to get the fractional cover if we're lacking sufficient spatial resolution or selecting perhaps the incorrect n members, which might work at one scale, but not as one tries to get a consistent result up and down. So I'd be interested in hearing perspectives on how we might make that a more well-determined problem.
Yeah, that's a great question. And of course, a lot of the unmixing algorithms assume that the data lies on a linear subspace so that you can actually reduce the number of degrees of freedom to make it tractable. But of course, that relies on getting the right n members. And as the pixels get coarser, the mixture, you get more and more mixing. So yeah, that's definitely a challenge. This is one area, ironically, where if the linear mixing model holds, as it does when the vertical relief of the surface is small relative to the size of the pixel, and you don't get a lot of multiple scattering, then in that case, it is actually fairly simple mathematically to scale it up or down to different sensors. Up at the top, yeah.
Yeah. I was surprised that you're recommending a reflectance product relative to topography. So in HyperNets, we're measuring land surface reflectance relative to the geoid. And we would always do that in a multi-mission context, because if you have to measure relative to topography, you'd be making a different measurement of downwelling irradiance for different spatial resolutions. So I'm surprised that you would want to have a satellite product relative to topography. I understand that the user will need to have that by the time it goes through an algorithm to get to something like a vegetation index. But if you're comparing between satellites, or comparing satellites to ground measurements, or even doing spatial averaging of satellite data, I would expect that it's better done relative to the geoid.
That's great feedback, and definitely something that we can consider in the working group, and it would be great to discuss in the breakouts or in a coffee break. I think one of the questions or thoughts that drove us in this direction is that really to calculate that downwelling irradiance accurately, one requires atmospheric information, and so there's a sense in which you can actually get a more accurate result by solving them both simultaneously, meaning it's helpful to have that done at the level 2A stage when you can still change the atmospheric state.
Okay, I disagree.
Question here, Chris Hacker from the University of Twente for Andreas Baumgartner, if he's still around. Yeah, so you mentioned that maybe the reducing or minimizing the keystone and the smile, spectral smile, as a design criteria might not the optimal way to go. As long as you can characterize your sensor properly to then calculate it away. Did I understand that correctly? And if so, what is the design criteria you would go for an optimal sensor that gives you the best results after the corrections you propose?
Yes, so what I showed is when you have more pixels, so to say, when you oversample, you have the information to do so, to interpolate. So if you look at atmospheric instruments that do this, in the instruments, they oversample in the spectral domain. And the technology is advanced, so you don't need to concern read noise that much anymore. And if you just use more pixels, you could actually then convert almost any sensor to another sensor. And so a lot of the questions or the problems in the last discussions can be solved in this way. You can create one standardized data product. And in Smile and Keystone, yet we are not of concern because you never can build a perfect instrument which is always the same. So then just ignore it, put more pixels in the instrument, And then you can reduce the data later, so to a certain degree. Does it answer the question? Okay, thank you.
I also have one question to David. You made the statement level 2A is fundamental, it is foundational, it is necessary for downstream processing attempts to measure Earth surface properties, which I fully agree. Then later on, I forgot if you say it has to be done or not, is the question of BRDF correction, so to correct for the different angles. Isn't this then an issue if we do this correction, we make assumptions on the Earth surface property, which makes it a bit problematic to derive it later on?
I think that, there are different perspectives here, of course, and I think there are lots of different valid choices one could make. Fundamentally, the quantity that we measure from the sensor is a directional quantity that comes from a specific observation direction. And so I think in SPG, I can speak for SPG anyway, that we'll be distributing those directional quantities with the notion that any simulation of alternative geometries would rely on modeling assumptions about the surface that may be user or discipline specific. And since I would argue there is no gold standard community solution to BRDF adjustment, I use the term adjustment rather than correction in this case, that we would distribute the quantity that we can be most sure about and then leave it as up to the user how they would prefer to interpret it.
Just to complement also on the CHIME side, at the moment our baseline is that we will not apply any BRDF correction.
I would have a second thing if there's time. It's more a comment. You also said, David, in your summary on the uncertainties, rigorous uncertainty quantification is needed to combine multi-mission data products in a principal way. I also fully agree to this, but I think it's not enough. For the measurement itself, the reflectances, you made very precisely what needs to be done, and I think we need to do the same for the uncertainty. If people include at best effort what they can, at the end we cannot combine them because some people have included elements which others have not. So putting it all in an equation when we do a multi-mission data set, we are comparing apples and bananas. I think we need to go further and specify it in the same way as done for the measurement.
I could not agree more. All right, with that, I'll hand it off to my colleague to discuss the results of our polling.
Okay, so regarding the question, how does your work contribute to improving harmonization? It seems that it is very important to harmonize data providing from different sensors. And so I think it is very important both for data format, data content, as I also said before in the presentation showed during this session. And also I think it would be very useful for the users to have available some multi-sensor, multi-mission system in order to gather and collect data from different sensors. So in this way, it will be very helpful for the user in order to compare and harmonize different data products for different sensors. From Italian Space Agency, we are also working about this approach. In particular, we are developing a multi-mission platform which involves Cosmos SkyMed and other sensors with the aim to collect data from different missions.
Can go maybe to the second question, Fabrizio. Thanks.
Okay, what aspect of harmonization can benefit user most? It seems that the make the data comparable is probably the best solution in this case, but I see a lot of different responses. I don't know if somebody has an additional comment about this point.
Maybe it's worth investigating more tomorrow in the breakout. It seems really a variety of different opinions, and yeah, so it's for further digging tomorrow. Yeah, maybe we go quickly through 3 and 4. Fabrizio, please. Thanks.
Yeah, clearly the majority of people think that the best level of processing where the harmonization is needed is surface reflectance, which means that earlier products, let's say 2R radians or things in level 1, this has a second priority, and higher levels beyond 2A also have a lower priority, which probably reflects the need that for most people, the surface reflectance is the starting point for the rest of applications. So having a good harmonization for level 2A is probably the thing that people are really looking for. I think that's the response that we were expecting, let's say. For the last one, we had the same situation because most of the people had said that harmonization on the information content of the product is the real important thing. When we set these questions, we already have in mind that the harmonization in data product is important, but it's not the driver because we can easily convert from one format to another. So this is not really the point. Although we must admit that the harmonization of the formats is the easy part. Which is more tricky and more difficult is the harmonization of the information content of the product. And it's really the place where we need to put all the focus. For instance, the discussion about this surface reflection has to be referred to the topography or to the geoid or other BRDF corrected or not, or all these kind of things basically are about the harmonization of the information content. What the information what the product provides as information, which is, I would say again, the expected answers. And so I am happy to see that there is a consensus in the community about these points. I don't know if somebody else want to add some additional comment.
I would suggest, if I may, looking at the time, that we keep talking over the icebreaker, because we basically 5 minutes, as of 5 minutes ago, it's set up already in Winter Garden, and we have to also walk there. I would take the last chance for another round of applause for the chairs and the speakers. Really, thank you very much. I think that this is a good starting point. This intentionally high-level questions are a good starting point for the discussion tomorrow. So we know where to focus. Now it's time, or tomorrow will be time, to dig a little bit deeper and understand where to focus, which are, let's say, of this information content, for example, just to take the last one, where do we have to focus our attention in the coming years? So thank you very much again. Let's walk to Winter Garden and have some relaxing food and drinks together.